There is a moment, standing at the ocean's edge, when the mind quiets. The rhythmic crash of waves, the vast blue expanse stretching toward the horizon. Something in us recognizes this place. Perhaps it's because we carry the ocean within us. The salt in our blood mirrors the salt in those ancient waters. Or perhaps it's because the ocean remembers what we've forgotten, that stillness can be strength, that patience can be power, that in the art of simply existing, there is profound wisdom. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. 4 billion years ago, long before continents took their current shapes, long before mountains rose or forests grew, Earth's ocean formed. Water vapor, released from volcanic eruptions across the young planet's surface, condensed in the cooling atmosphere. Rain fell for millennia. The ocean filled Earth's low-lying basins, creating a single vast body of water that would become the cradle of all life. In those ancient waters, chemistry became biology. Simple molecules collided, combined, separated. Energy from hydrothermal vents on the seafloor drove reactions that built increasingly complex structures. And then, somehow, through processes we're still working to fully understand, molecules began to replicate themselves. Life emerged, not on land which was barren and inhospitable, but in the ocean, where water's embrace provided everything the first living cells required. Consider what water offered these primordial organisms. Buoyancy, freedom from gravity's relentless pull. On land, every creature must expend enormous energy simply standing upright, resisting collapse. But in water, density provides support. A single-celled organism floats suspended, held aloft by the medium itself. This fundamental property of water, that it holds things up, created the first condition for tranquility to evolve not as luxury, but as survival strategy. The ocean's physics writes rules unlike those governing terrestrial life. Water molecules cling to one another through hydrogen bonds, creating surface tension at the boundary between water and air. Creatures discovered they could rest at this interface, supported from below by the water's density, held together from above by molecular attraction. The physics of water created opportunities for stillness. Density itself varies throughout the ocean's depths. Saltwater becomes denser with increasing salinity. It becomes denser still with decreasing temperature. These variations create invisible layers throughout the ocean column, zones where water of one density meets water of another. And at these boundaries, creatures discovered they could hover motionless, perfectly balanced between the denser water below and the lighter water above. Neutral buoyancy. The ocean handed evolution a gift, the ability to exist in 3 dimensions without falling. Light behaves differently in water than in air. In air, light travels until something blocks it. In water, light penetrates only so far before the water itself absorbs it. The brightest wavelengths, reds and oranges, vanish within the first few meters. Yellows fade deeper down. Only blues and greens penetrate to 200 meters depth, creating the ocean's characteristic azure hue. Beyond 200 meters, darkness reigns. This decreasing light created zones of existence, each with its own character. The sunlit surface waters, called the epipelagic zone, where photosynthesis occurs and life thrives in abundance. The twilight zone below, the mesopelagic, where faint blue light creates a realm of shadows. And deeper still, the bathypelagic, the midnight zone, where no sunlight ever reaches, where eyes become useless, where life evolved other senses to navigate eternal night. In the deepest darkness, movement slowed to match the dimming world. When sight offers no advantage, speed becomes wasteful. Efficiency replaced urgency. Temperature, too, stratifies the ocean. Surface waters warm under tropical suns, reaching 28 or 30 degrees Celsius. But heat doesn't penetrate deeply. Within a few hundred meters, temperature plunges. At a boundary called the thermocline, temperature drops sharply over a relatively short distance. Below the thermocline, cold water fills the deep ocean, 4 degrees Celsius or less, maintaining temperatures barely above freezing regardless of what happens at the surface. These temperature bands create stable homes where conditions barely change across centuries. Stability allows creatures to specialize, to perfect strategies for existence in environments that remain predictably constant. And sound. In air, sound waves travel at approximately 340 meters per second, dissipating quickly as molecules scatter the vibrations. But in water, sound travels 4 times faster, 1,500 meters per second. And it travels farther, much farther. The ocean becomes an acoustic cathedral where a whale's song, produced by vibrations in the animal's larynx, can travel 5,000 miles before fading to silence. Communication across continents, achieved without movement, without approaching, simply by making sound in a medium that carries those vibrations across vast distances. The sperm whale demonstrates the ocean's acoustic nature spectacularly. This enormous creature, males reaching 18 meters in length, weighing up to 57,000 kilograms, produces clicks that measure 200 decibels, making them the loudest sounds produced by any animal on Earth. 200 decibels. Loud enough that some researchers theorize the sound itself might stun prey through acoustic force, though the evidence remains inconclusive. Yet despite producing these extraordinarily loud clicks, the sperm whale remains serene. It hangs vertically in the water column during rest periods, head pointing down toward the abyss, tail toward the distant surface. The whale sleeps this way, motionless, suspended between depths. Discovered only in the early 2000s, this vertical sleeping behavior revealed something profound about ocean life. That even apex predators, enormous beyond terrestrial comparison, have perfected the art of stillness. In this environment, buoyant, stratified, acoustically connected, increasingly dark with depth, life began its experiments in existence. And among the earliest successes were creatures that would perfect stillness to an art form that persists, essentially unchanged, across 500 million years: the jellyfish. Consider this animal for a moment. It emerged 500 million years ago, before fish evolved, before complex eyes developed, before bones existed. The first jellyfish pulsed through Cambrian seas when life was still working out basic body plans. And that body plan, radially symmetrical, composed of 95% water, possessing a simple nerve net rather than a brain, trailing tentacles like silk, proved so effective that jellies have remained essentially unchanged through 500 million years of Earth's transformations. The jellyfish requires no complex systems because it mastered efficiency at the most fundamental level. Its body contains 2 cell layers separated by a jelly-like middle layer called mesoglea. The outer layer, epidermis, interfaces with the ocean. The inner layer, gastrodermis, lines the digestive cavity. Between them, the mesoglea provides structure, not through rigid skeleton but through being mostly water, incompressible and thus shape-maintaining. To move, the jellyfish contracts muscles lining its bell. The contraction expels water, propelling the animal forward. Then the muscles relax. Water flows back in, refilling the bell through simple pressure differentials. The jelly drifts upward on the force of that expelled water, then sinks as the bell refills. Pulse, drift, 40 to 60 times per minute, a rhythm close to a resting human heart rate. The jellyfish repeats this pattern, and between pulses, between those muscle contractions, the jellyfish simply exists. It doesn't decide where to go, currents carry it. It doesn't hunt actively. Prey drifts into trailing tentacles, which fire stinging cells called nematocysts automatically upon contact. The jellyfish doesn't flee predators actively. Many predators ignore jellies because their bodies contain so little nutrition. The jellyfish surrenders to the ocean's movements, participating in the larger flows, going wherever water carries it. Moon jellies, Aurelia aurita, gather in blooms numbering thousands of individuals. These aggregations create underwater clouds, each jelly pulsing at its own rhythm, yet the overall effect appearing synchronized, as though the bloom breathes as a single organism. Watching this, one confronts a question about consciousness itself. The jellyfish has no brain. Its nervous system consists of nerve nets, diffuse webs of neurons spread throughout its body. Yet somehow, these simple nets coordinate muscle contractions, regulate pulsing rhythm, process information from light-sensitive spots called ocelli, and trigger tentacle stinging. A living meditation on repetition and rhythm, the jellyfish demonstrates that complexity isn't required for survival, for persistence across 500 million years, for perfecting tranquility. The nautilus represents a different ancient solution. This cephalopod mollusk, related distantly to octopuses and squid, encases its soft body in a hard spiral shell divided into chambers. The shell spiral follows mathematical perfection. Each new chamber, added as the nautilus grows, is larger than the previous chamber by exactly the same ratio, approximately 1.618. This ratio, called the golden ratio, appears throughout nature, in spiral galaxies, in hurricane formations, in the arrangement of seeds in sunflowers. The nautilus has constructed shells following this ratio for 480 million years. Inside this mathematically perfect shell, the nautilus manipulates buoyancy with precision. The chambers behind its body contain gas and fluid in carefully controlled ratios. To rise from the depths where it spends daylight hours, 400 meters down, in darkness and cold, the nautilus adjusts the fluid levels in its chambers, increasing the gas ratio. Buoyancy increases. The nautilus rises effortlessly towards shallower waters where it hunts at night. To descend as dawn approaches, it reverses the process, increasing fluid ratio. Negative buoyancy pulls it downward. The nautilus sinks back to depth where it rests during daylight. Safe from visual predators in the darkness, this nightly migration, vertical rather than horizontal, measured in hundreds of meters rather than thousands of miles, occurs without urgency. The nautilus moves slowly, propelling itself by drawing water into its body cavity and expelling it through a flexible funnel. The jet propulsion pushes it forward, but nautilus swimming appears more like drifting with intention rather than purposeful locomotion. Its eyes, pinhole cameras, the simplest possible eye structure, have no lens, no way to focus. Images form on its retina through the pinhole effect alone, as light streams through the small opening. These eyes, unchanged since the Ordovician period 480 million years ago, when continents were arranged so differently that Earth would be unrecognizable to us, gather enough information for the nautilus to navigate and hunt. Perfection, it seems, doesn't require complexity. The hagfish explores another extreme of ancient calm. Unchanged for 300 million years, this jawless fish represents one of the oldest surviving vertebrate lineages. It possesses a skull, but no vertebral column. Instead, a notochord, a flexible rod of tissue, provides structural support. The hagfish has 4 hearts, one main heart, and 3 accessory hearts that assist in moving blood through its long, eel-like body. The main heart beats without input from any brain. It continues rhythmically on its own, paced by internal properties of the heart muscle itself rather than external commands. When disturbed, grabbed by a predator, handled by a curious researcher, the hagfish produces slime. Not ordinary slime, but a remarkable substance produced through specialized glands lining its body. The glands release threads made of protein, along with mucus. When these components contact seawater, the threads instantly unravel, each thread expanding to 10,000 times its original length in milliseconds. The threads entangle, the mucus absorbs water, and suddenly the hagfish has produced up to a liter of thick fibrous slime from a tiny amount of precursor material. The slime clogs predator gills. It makes the hagfish impossibly slippery to hold, yet the hagfish itself remains utterly unbothered by its own defensive production. To escape the slime, which would suffocate the hagfish as surely as it suffocates predators. The hagfish ties its body into a knot. It slides the knot from tail toward head, scraping off the slime as the knot travels forward. The same knot-tying behavior helps it gain leverage while burrowing into carrion, dead whales on the seafloor, fallen fish, anything it can scavenge. The hagfish doesn't hunt. It doesn't flee. It simply exists, scavenging whatever the ocean provides, surviving 20 hours without oxygen when necessary by lowering its metabolism to near dormancy. Patience as a fundamental life strategy refined across 300 million years. In the perpetual night beyond 200 meters depth, where no sunlight ever penetrates, the anglerfish evolved to practice predation through stillness. The female anglerfish, larger than the male, responsible for hunting, positions herself in darkness. From a modified dorsal spine extending forward above her mouth dangles a fleshy lure. And in this lure, bacteria live. Bioluminescent bacteria that produce light through chemical reactions, combining luciferin molecules with oxygen in the presence of the enzyme luciferase. The reaction releases energy as light, cold light, producing illumination without heat. This beacon glows in the darkness. Small fish and crustaceans, attracted to light in an environment where light rarely appears, approach. The anglerfish waits. She might wait hours, days. Her metabolism runs slowly enough to survive on rare meals. She doesn't chase. She doesn't search. The lure brings prey to her. When prey ventures close enough, her mouth opens. But not through speed, through vacuum. Sudden expansion of the mouth cavity creates negative pressure. Water rushes in to fill that vacuum, carrying prey with it. The entire strike takes 40 milliseconds. Then the mouth closes. The prey has been consumed, and stillness returns. The male anglerfish follows a different strategy entirely. Small, sometimes 10 times smaller than the female, the male searches through darkness for a female. When he locates one, he bites into her body. His mouth fuses with her flesh. Their circulatory systems merge. The male loses his digestive system, his eyes, his heart, everything unnecessary once he has found a female. He becomes essentially a sperm-producing appendage, permanently attached, sharing her bloodstream, fertilizing her eggs when she's ready to spawn. This is partnership reduced to its essence, not competing, not even cooperating exactly, but becoming a single entity, two bodies sharing one patient existence in the darkness, waiting for prey to arrive at a glowing lure, embodying an extreme form of energy conservation that only makes sense in an environment where food is scarce and finding mates is difficult. These ancient ones, jellyfish, nautilus, hagfish, anglerfish, represent life's early experiments in existence. And what they discovered, what evolution proved effective across hundreds of millions of years, was this: in the ocean's embrace, stillness works. Efficiency surpasses frantic activity. Patience becomes strategy. The water provides support. The darkness removes the need for constant vigilance. The stability allows for slow metabolisms, rare meals, long lives spent drifting, waiting, existing without urgency. When we observe these creatures in aquariums, through documentary footage, in person if we're fortunate enough to dive or submarine into their realms, something in us responds. Our heart rate's slow, our breathing deepens, the constant mental chatter quiets, just for a moment. We're witnessing what life looks like when it has perfected the art of being rather than doing. When it has discovered that survival doesn't require constant struggle, but can instead be a slow dance with fundamental forces. The ocean, covering 71% of Earth's surface, represents a realm operating on principles fundamentally different from terrestrial existence, and the creatures within it, creatures that learn to float, that learn to hover, that learn that stillness can be strength, offer us something we desperately need. They remind us that peace isn't the absence of life, but can be its most refined expression. That patience isn't passive, but can be a strategy refined across millions of years. that in a universe often appearing chaotic and urgent, there exist ways of being that are unhurried, efficient, and graceful. 4 billion years of evolutionary wisdom swims in those waters, and as we prepare to descend deeper into their realm, to meet the creatures that migrate without hurry, the bodies built for stillness, the hunters who wait, we carry with us this first lesson, that water taught life how to float. And in floating, life discovered tranquility. The grey whale embarks on one of nature's most extraordinary journeys. 12,000 miles round trip. From Arctic feeding grounds in the Bering and Chukchi Seas down the Pacific coast of North America to the warm lagoons of Baja California, Mexico, and back again. 12,000 miles. To put that in perspective, that's roughly halfway around Earth's circumference. A journey that would take a human walking 8 hours daily nearly 2 years to complete. Yet the grey whale accomplishes this migration annually, and it does so without hurry. These whales travel at 5 miles per hour, a pace barely faster than a human's casual walk. They hug coastlines, following the continent's edge, sometimes so close that observers on shore can watch them passing. They don't swim continuously. Sometimes they rest in kelp forests, their massive bodies, reaching 15 meters in length, weighing 35,000 kilograms, settling into the swaying underwater meadows. Sometimes they pause to feed on small prey in shallow waters. Sometimes they simply drift, letting currents carry them while they rest. Mothers with newborn calves travel even more slowly, 3 miles per hour. The calf, born in the warm Mexican lagoons, weighing perhaps 900 kilograms and measuring 4 to 5 meters long, must surface to breathe every 3 to 5 minutes. The mother adjusts her pace to match, swimming slowly enough that her calf can keep up, surfacing when the calf needs air, protecting this vulnerable youngster as they journey together through 6,000 miles of ocean to reach Arctic feeding grounds. The migration takes 3 months each direction, half the year spent traveling, and during this journey the whales barely eat. They live off blubber reserves accumulated during the previous summer's feeding season in the Arctic, where they consumed vast quantities of amphipods, small shrimp-like crustaceans from the seafloor. A grey whale might eat 1,300 to 1,800 kilograms of food daily during peak feeding season, storing energy as blubber that will sustain it through migration and breeding. How do they navigate? How does a whale swimming through featureless ocean, often out of sight of land, know which direction leads home? We're only beginning to understand. Research suggests whales use Earth's magnetic field, sensing subtle variations in magnetic intensity that create an invisible map spanning entire oceans. The planet's magnetic field isn't uniform. It varies based on the magnetic properties of underlying geology, creating magnetic contours that a whale might follow like a road. They also follow geographical features invisible from the surface but present on the seafloor, underwater canyons, seamounts, underwater mountains that rise from the ocean floor but don't break the surface, continental shelf edges where shallow coastal waters drop away to deep ocean. These features create patterns in water movement, temperature, and acoustic properties that whales might perceive and remember. And perhaps most remarkably, navigation appears to be cultural. Whale populations follow specific routes passed down through generations. Young whales learn the migration path by traveling with their mothers and other adults, observing, internalizing the journey. Grey whales off California's coast follow different routes than grey whales off Korea's coast, despite being the same species. Each population maintains its own traditional pathways, knowledge transmitted not through genetics but through teaching, a form of culture in creatures whose brains are, in many ways, organized quite differently from our own. The journey itself becomes meditation. Breathing, swimming, a rhythm sustained across months and thousands of miles, and at journey's end, warm lagoons where females give birth, Arctic waters rich with food, familiar places where generations before have arrived, rested, and prepared for the return journey. The grey whale demonstrates that distance means nothing without urgency, that 12,000 miles traveled at 5 miles per hour becomes simply what one does year after year, because this is how grey whales exist. The sea turtle's migration matches the whales for patience, but surpasses it in precision, and in the mystery of how such precision becomes possible. Consider the loggerhead sea turtle. She hatches on a beach in Florida, one hatchling among hundreds, emerging simultaneously from nests buried in sand. The hatchlings, each weighing perhaps 20 grams, small enough to fit in a human palm, scramble toward the ocean, guided by the brightness of the horizon over water, contrasting with the darkness of land. They enter the surf. Waves larger than their entire bodies tumble them. They swim frantically, reaching the open ocean exhausted but alive. And then she disappears. For 10 to 30 years, this turtle travels. Currents carry her across the Atlantic. Ocean to feeding grounds near Africa. The Azores, the Cape Verde Islands, the coast of West Africa. She drifts through the Sargasso Sea, that vast area of the North Atlantic characterized by floating mats of sargassum seaweed, calm waters, and rotating currents called gyres. She grows slowly, eating jellyfish and crustaceans, surviving predators, gradually accumulating size and strength. From 20 grams at hatching to perhaps 130 kilograms as an adult female. When she reaches sexual maturity, 30 years after hatching, perhaps longer, instinct older than mountains calls her home. She begins the return journey, 3,000 miles across the Atlantic Ocean, and she swims steadily, unhurried back to Florida, back to the beach where she hatched, sometimes to within meters of the exact spot where her own nest was buried 3 decades earlier. How does a turtle, having never returned to her birth beach in 30 years, navigate precisely back to a specific stretch of coastline? The journey demonstrates navigation so precise it seems impossible, yet thousands of turtles accomplish it annually. Researchers have discovered sea turtles can detect Earth's magnetic field with extraordinary sensitivity. But more than that, they can detect subtle variations in magnetic field strength and inclination angle. Every location on Earth has a unique magnetic signature combining field intensity and the angle at which field lines intersect Earth's surface. Sea turtles imprint on the magnetic signature of their birth beach as hatchlings. 30 years later, that imprinted signature calls them home, but the journey itself, 3,000 miles of open ocean, happens without hurry. The loggerhead travels steadily, breathing once every 4 to 7 hours while underwater. Her heart slows to conserve oxygen. Her metabolism operates at rates that allow her to rest while swimming, to move while conserving energy, to cross an ocean over months rather than days. This is tranquility as endurance, not excitement, not urgency, but patient progression, sustained across vast distances and decades of time. When she arrives at her birth beach, she emerges from the surf at night. She crawls above the high tide line using her front flippers, leaving a track in the sand. She digs a nest cavity using her rear flippers, excavating precisely, creating a flask-shaped chamber deep in the sand. She lays approximately 100 eggs. Then she covers the nest, disguising its location, and returns to the ocean. She'll repeat this process 3 to 5 times during the nesting season, then return to feeding grounds thousands of miles away. 2 to 3 years will pass before she makes this journey again. The eggs incubate for 60 days. Temperature determines the sex of developing turtles. Warmer temperatures produce females, cooler temperatures produce males. When ready to hatch, the baby turtles pip through their shells, dig upward through sand, and emerge at night, timing their emergence to avoid daytime predators and daytime heat. They scramble toward the ocean, entering the surf, beginning the journey their mother completed decades earlier. Those that survive, perhaps 1 in 1,000 hatchlings, will spend their first years drifting. The North Atlantic Gyre, a massive circular current system spanning thousands of miles, becomes nursery to to millions of young sea turtles. The Sargasso Sea at the Gyre's center holds them in its gentle rotation. They drift through floating sargassum, eating what they can catch, growing slowly, moving with currents that require no swimming, no navigation, no effort beyond patient existence. The ocean cares for them, asking only that they drift and grow and survive until they're large enough to actively migrate. If the sea turtle demonstrates precision, the salmon demonstrates transformation. Sockeye salmon hatch in freshwater streams, often tributaries of larger rivers, in gravel beds where their parents spawned and died. The young salmon, called alevins at this stage, remain in the gravel for weeks, absorbing yolk sacs that provide nutrition. When the yolk sacs are depleted, they emerge from the gravel as tiny fish equipped with instinct to swim downstream. They spend a year or two in fresh water, sometimes in streams, more often in lakes, growing, feeding, becoming strong enough for ocean life. Then, as smolts weighing perhaps 20 to 30 grams, they feel the call to descend to the ocean. They travel downstream, their bodies undergoing physiological changes called smoltification that prepare them for salt water. Their kidneys adjust to process salt. Their gills adapt to excrete excess salt rather than retain it. Their bodies become streamlined, their coloring shifts from the camouflage patterns useful in streams to the silver coloring that provides some protection in open ocean. They reach the ocean and disappear into vastness. The North Pacific becomes their home. Some travel to the Gulf of Alaska, 5,000 miles from their birth streams. They feed on zooplankton, small fish, anything they can catch. They grow, from fingerlings to adults weighing 5 to 8 pounds, sometimes more. They spend 2 to 3 years in the ocean, accumulating energy, building strength, preparing for a return journey they don't consciously know they must make. Then the return journey begins. The salmon navigate using smell, recognizing the chemical signature of their birth stream stored in memory since they were juveniles. Each stream has a unique chemical profile determined by the minerals in surrounding rocks, the vegetation along banks, the particular mixture of organic compounds that water absorbs as it flows toward the sea. Salmon remember this signature. Years later, having traveled thousands of miles through ocean, they recognize the scent dissolved in water and follow it home. As they enter fresh water, their bodies begin transforming. They stop eating entirely. From this moment forward, sometimes, weeks from their spawning grounds, they will consume nothing. They live off stored fat, their bodies metabolizing muscle tissue when fat runs out. Males develop hooked jaws called kypes and humped backs. Both sexes turn from silver to deep red, their bodies taking on the brilliant coloration that gives sockeye their name. These changes occur as they swim upstream, against currents, up waterfalls, through rapids. Traveling 10 to 30 miles per day, they push forward. At waterfalls, they leap, launching themselves from the water, sometimes clearing falls several meters high, sometimes failing and trying again, repeatedly, until they succeed or die trying. The journey exhausts them. Their bodies deteriorate, but they continue, driven by instinct to reach the exact gravel beds where they hatched. When they arrive, battered and exhausted, spawning begins. Females dig nests using their tails, creating depressions in the gravel. Males compete for spawning rights, the largest and strongest defending access to the females. The female releases eggs into the nest. The male releases milt to fertilize them. The female covers the eggs with gravel, creating a protective mound called a redd. And then, within days, both parents die. Their bodies drift in the current or wash onto banks. Bears drag carcasses into forests. Eagles and ravens feed on the remains. The bodies decompose, releasing nutrients, nitrogen, phosphorus, marine-derived nutrients that have traveled from ocean to stream. These nutrients fertilize the stream ecosystem, feeding algae and invertebrates that will feed the next generation of young salmon. The parents die, but in dying, they feed the very environment their offspring will need to survive. The journey demonstrates tranquility as determined persistence. Not frantic urgency, but steady progression toward an inevitable conclusion. The salmon doesn't rush. It can't rush. Its body is transforming, deteriorating, investing everything in this final journey. But it continues, patient in its determination, embodying a form of calm that exists even in the face of approaching death. The European eel inverts the salmon's journey, living in fresh water but breeding in ocean depths. These eels spend 20 to 40 years in rivers and lakes across Europe, growing slowly, reaching lengths of 1 meter or more. Then as adults they feel the breeding call. They swim downstream, enter the ocean, and begin a migration of 3,000 miles to the Sargasso Sea, the same region that serves as nursery for sea turtle hatchlings. In the Sargasso Sea, at depths of 400 to 700 meters, European eels spawn and die. The entire adult population perishes after breeding, their death programmed, inevitable, the culmination of decades of life spent in fresh water. But their eggs hatch in the ocean, producing leaf-shaped larvae called leptocephali. These larvae, transparent, looking nothing like adult eels, drift for 3 years on ocean currents back toward European coasts. The journey takes 3 years. The larvae don't swim actively. They drift, feeding on marine snow, growing slowly, moving with currents in a journey that spans a third of their lives. When they approach European coasts, they metamorphose into glass eels, still transparent but now eel-shaped. These glass eels enter rivers, swimming upstream, establishing territories in freshwater where they'll spend the next 20 to 40 years, before making the return journey to spawn and die. This migration remained completely unknown to humans until the early 20th century. Aristotle thought eels arose spontaneously from mud. Medieval scholars had various theories, that eels rubbed against rocks and the friction created young eels, that they emerged from morning dew. The truth, that these abundant freshwater fish migrate thousands of miles to ocean depths to spawn, remained hidden despite eels' ubiquity, despite humans catching and eating them for millennia. The eel kept its secret, generation after generation making the journey, until scientific advances finally revealed their hidden life cycle. The garden eel demonstrates that migration can be measured in inches rather than miles, and still embody tranquility perfectly. These pencil-thin fish, perhaps 40 centimeters long but only as thick as a finger, live in colonies numbering thousands. Each individual digs a burrow in sandy seafloor, reinforcing the burrow walls with mucus secreted from its skin. The burrow becomes permanent home. The eel never leaves it entirely. Instead, it extends its body upward from the burrow, 2/3 of its length emerging, while the tail remains anchored below. Extended into the current, the garden eel sways. Like seagrass, like kelp, it angles its body into water flow, opens its mouth, and filter feeds on zooplankton carried past by currents. The current brings food directly to it. The eel simply waits, mouth open, filtering what the ocean provides. Hours pass this way, days. The eel swaying continuously, feeding continuously, never moving from its spot. When threatened, a predator approaches. A shadow passes overhead. The garden eel retreats. The colony disappears in a synchronized wave, thousands of individuals pulling back into their burrows in seconds. The sandy plain that moments before appeared like an underwater forest of swaying stems suddenly shows no sign of eels. They wait below until danger passes. Then gradually they re-emerge. The forest of swaying bodies reappears. Reading resumes, the same individual occupies the same burrow for years. Neighbors maintain spacing of approximately 1 body length, close enough for a sense of colony, far enough to avoid competing for the same patch of current. The colony creates patterns across the seafloor, each eel positioned optimally, all swaying together, creating what looks like synchronized dance, but is actually each individual responding independently to the same water flow. This is migration through time rather than space. The garden eel doesn't travel. It establishes a position and maintains it across years, participating in life by simply being present, swaying in the current, taking what comes. Stationary migration, a journey measured not in miles but in patience, in the accumulation of days spent filtering food from passing water. In the quiet persistence of remaining, the spiny lobster demonstrates yet another form of migration, walking in single file across the seafloor. When autumn storms arrive in the Caribbean, spiny lobsters emerge from reef crevices where they've spent the calm season. They gather, dozens of individuals assembling spontaneously. Then they form a queue. Each lobster places its antennae on the tail fan of the lobster ahead. The line forms, sometimes containing 65 individuals, and begins marching. They walk across open sand toward deeper water, traveling up to 30 miles. The journey takes days. They walk continuously, maintaining formation, moving as one coordinated entity. If the line breaks, if something separates one segment from another, both segments stop. They wait. Eventually the segments reconnect, the queue reforms, and the migration continues. Traveling in single file provides advantages. The lobster at the front breaks the current, creating a slipstream that reduces drag for followers. The queue deters predators. A lone lobster is vulnerable, but a line of 65 lobsters presents a challenging target, especially since lobsters possess formidable spines and can strike with their antennae if threatened. The migration to deeper water may protect them from storm turbulence affecting shallow reefs. The behavior demonstrates that even arthropods with simple nervous systems can coordinate complex group behaviors. No leader directs the migration. No lobster possesses an overview of the entire queue. Yet somehow, through local interactions, each lobster maintaining contact with the one ahead, the entire line coordinates its movement, finding safety through group patience rather than individual speed. These migrations, whale journeys spanning oceans, turtle returns to birth beaches after decades, salmon transformations from ocean silver to stream red, eel mysteries spanning continents garden, eel stillness measured in years. Lobster queues walking across seafloor demonstrate a quality of existence rarely found in terrestrial life. Migration without hurry, travel as meditation. Distance and time become simply what unfolds when living creatures follow patterns refined across millions of years. Watch a gray whale mother and calf swimming south along the coast. 5 miles per hour, 3,000 miles to go, 3 months of travel ahead. Yet neither whale appears concerned. They swim, they breathe, they rest in kelp forests. They arrive when they arrive. The journey itself is the life, and the life is patient. This patience, this absence of urgency, despite vast distances, stems from the same source as the stillness we discovered in the previous chapter. The ocean provides. Buoyancy supports massive bodies without requiring energy expenditure. Currents assist rather than impede if you surrender to them. Navigation happens through senses we barely understand. Magnetic field detection, chemical signatures, acoustic properties, making the journey less about finding the way and more about recognizing where you are. And in recognizing these migrations, in understanding that 12,000 miles can be traveled without hurry, that 30 years can pass between leaving and returning to the same beach, that death itself can be approached with calm determination, we encounter again that lesson the ocean teaches. That time is vast. That patience outlasts speed. That arriving matters less than the quality of the journey. That existence, practiced with efficiency and grace, becomes its own reward. The migrations continue as they have for millions of years, as they will for millions more if we allow them to persist. And in their continuation, they offer us something we desperately need, proof that there are other ways to move through the world. That urgency isn't necessary. That vast distances become manageable when divided into patient increments. That home exists not just as destination, but as memory carried within, calling us forward through whatever journeys we must make. The blue whale's heart weighs 400 pounds. 400 pounds of muscle organized into chambers, designed to pump blood through the largest animal ever to exist on Earth. At the surface, breathing easily, this massive heart beats 5 to 6 times per minute. 5 beats, 6 beats, then a pause, then another beat. The rhythm moves slow enough that if you could hear it, you could count between beats 1, 2, 3, 4, 5, measuring the intervals in which the largest heart on Earth rests between contractions. But when the blue whale dives, descending to depths of 500 meters, staying submerged for 20 minutes, the heart slows further. 2 beats per minute, 1 beat every 30 seconds. For half a minute, the heart rests. Then it contracts once, sending blood through a body weighing 200 tons. Then it rests again. How is this possible? How does a creature of this size survive on 2 heartbeats per minute? The answer lies in adaptation refined across millions of years. As the whale dives, blood flow redirects. Vessels supplying extremities constrict. Blood flows primarily to the brain and vital organs. The heart itself, the lungs before they collapse under pressure, the liver, the kidneys. Everything else can wait. The massive muscles powering the tail flukes operate on stored oxygen rather than continuous blood flow. Those muscles contain high concentrations of myoglobin, a protein similar to hemoglobin, but specialized for storing oxygen in muscle tissue. Myoglobin gives whale meat its deep red, almost purple color. It allows muscles to continue working even when blood supply is restricted. The whale can shut down non-essential functions, becoming a living submarine optimized for depth and duration. It achieves a state of efficiency that seems impossible for an animal of this scale. 200 tons, more than 30 elephants, a heart weighing as much as a grand piano. Yet during dives, this enormous system operates on minimal cardiac activity, demonstrating that size doesn't demand constant metabolic intensity if the body is designed correctly, and the body is designed correctly, streamlined. The blue whale's shape creates minimal drag despite its enormous size. Water flows smoothly along its body, separating cleanly at the tail, creating relatively little turbulence. The massive tail flukes, spanning 7 meters in width, provide thrust with slow, powerful strokes. Up and down, unlike fishtails which move side to side, each stroke propels the whale forward. Between strokes, the whale glides, momentum carrying it onward, while the tail resets for the next stroke. During casual swimming, the blue whale travels at 5 miles per hour, leisurely, unhurried. This represents cruising speed, the pace at which the whale covers vast distances while expending minimal energy. It can accelerate to 20 miles per hour in short bursts when necessary, when avoiding ships, when competing for mates. But such speed depletes energy reserves quickly. The efficient pace, the sustainable pace, is 5 miles per hour. At that speed, buoyancy supports its weight, streamlining minimizes drag, and slow tail strokes provide steady propulsion. This enormous size becomes possible because water provides buoyancy. Consider what would happen if you could somehow place a blue whale on land. The weight would be catastrophic. 200 tons of mass, suddenly unsupported by water's buoyancy, pressing down on bones and organs. The skeleton would collapse. Ribs would crack under the weight of internal organs. The heart couldn't pump blood against gravity through such a massive body. The whale would suffocate under its own weight, lungs compressed, unable to expand for breathing. Death would come quickly, but in water, weight becomes nearly irrelevant. Archimedes discovered the principle 2,000 years ago, though humans understood it intuitively long before. Any object immersed in fluid experiences an upward force equal to the weight of fluid displaced. For the blue whale, displacing 200 tons of water, this means experiencing an upward force of 200 tons. Weight and buoyancy balance perfectly. The whale hovers, suspended, requiring minimal energy to maintain position. Only the energy to move forward matters, and streamlined shape minimizes that requirement. The sperm whale pushes this adaptation even further, diving to 3,000 meters, nearly 2 miles straight down into darkness, where pressure reaches 300 times atmospheric pressure at the surface. These dives last 90 minutes without breathing. 90 minutes in cold darkness, hunting giant squid in the deep scattering layer where bioluminescent creatures create false starfields in the abyss. How does the sperm whale survive these extreme dives? First, the lungs collapse. As pressure increases during descent, the lungs compress completely, expelling all air. This prevents nitrogen in the air from dissolving into the blood at high pressure, nitrogen that would form dangerous bubbles during ascent, causing decompression sickness, the bends that affects human divers who ascend too quickly. By collapsing the lungs and expelling air, the sperm whale eliminates this risk. But without air in the lungs, where does oxygen come from? The blood and muscles. Sperm whale blood contains high concentrations of hemoglobin, binding oxygen molecules to carry them throughout the body. The muscles contain even higher concentrations of myoglobin. Together, blood and muscle tissue store enough oxygen to sustain the whale for 90 minutes of submersion. The sperm whale's body contains another remarkable adaptation, a massive organ in its head comprising up to 1/3 of the animal's total body length. This organ contains spermaceti oil, a liquid wax that gives the sperm whale its name. Early whalers thought it was the whale's sperm. The function of spermaceti oil remained mysterious for centuries. Modern research suggests it may help regulate buoyancy. The whale can adjust blood flow to the spermaceti organ, warming or cooling the oil. Warm oil expands, becoming less dense, increasing buoyancy. Cool oil contracts, becoming denser, decreasing buoyancy. By controlling oil temperature, the whale might adjust its buoyancy at different depths without expending energy swimming. After 90 minutes at depth, the sperm whale ascends slowly. It surfaces, breathes deeply 7 to 10 times, rapid, powerful exhalations and inhalations, replenishing oxygen stores, then dives again. This cycle repeats throughout the whale's 50 to 70-year lifespan. Dive, hunt, surface, breathe, dive. A rhythm as regular as breathing itself, though measured in hours rather than seconds, between deep dives. Sperm whales engage in behavior discovered only in the early 2000s. Behavior so extraordinary, it seems impossible until you see the photographs. They sleep vertically. Groups of whales gather in pods. They position themselves heads up or heads down. Different individuals adopt different orientations and hang motionless in the water column, utterly still, not swimming, not adjusting position, simply suspended like enormous buildings floating in blue space, maintaining depth through perfect neutral buoyancy. They remain this way for 10 to 15 minutes at a time. During these intervals, they appear completely unconscious. Researchers approaching in boats have gotten within meters of sleeping sperm whales without the animals responding. No reaction to engine noise, no response to the boat's presence. True sleep, not merely rest. How they avoid predators during these vulnerable periods remains unknown. How they know when to surface for air, whether some internal clock triggers awakening, whether decreasing oxygen levels rouse them, remains mysterious. But the behavior itself, captured in photographs by underwater photographer Franco Banfi, became one of the most striking images of ocean tranquility ever documented. Half a dozen sperm whales, each weighing 40 to 50 tons, each measuring up to 18 meters long, hanging vertically in blue water, utterly still. Like skyscrapers suspended in space, dolphins and other toothed whales solved the sleep challenge differently. They practice unihemispheric sleep, sleeping with half the brain at a time. During rest periods, a dolphin closes one eye. The opposite brain hemisphere shows sleep patterns on EEG measurements, the characteristic slow waves indicating deep sleep. Yet the animal continues swimming. It surfaces to breathe. It maintains awareness of surroundings through its open eye and wakeful brain hemisphere. After approximately 2 hours, the sides switch. The sleeping hemisphere wakes. The wakeful hemisphere sleeps. The other eye closes while the first eye opens. This adaptation means dolphins never fully lose consciousness. They never stop moving, yet they still achieve the restoration sleep provides. Both brain hemispheres get their required rest, just not simultaneously. The strategy allows continuous swimming, necessary for animals that must surface to breathe, that can't afford to sink while unconscious. It allows constant vigilance, at least half the brain always monitoring for predators, for prey, for the social cues that maintain pod cohesion. Mothers with newborn calves take this adaptation to an extreme. For the first month after giving birth, mothers don't sleep at all. Both brain hemispheres remain continuously active. The calf needs constant attention. It must learn to swim properly, must surface frequently to breathe, must stay close to its mother for protection. Only after the calf matures somewhat does the mother gradually resume unihemispheric sleep patterns. Catching rest when the calf becomes more independent, the sea otter represents a different challenge, living in cold water without the insulating blubber that protects whales, dolphins, and seals. Instead, sea otters depend entirely on fur, not ordinary fur, but the densest fur of any mammal, up to 1 million hairs per square inch. By comparison, humans have roughly 100,000 hairs on their entire head. The otter has 10 times that number in a single square inch of fur. This incredible density creates a layer of trapped air next to the skin. Water never touches the otter's skin if the fur remains properly maintained. The trapped air insulates, keeping body heat from escaping into cold water, but the system requires constant maintenance. Otters spend 3 to 5 hours daily grooming. They meticulously separate hairs, ensuring they remain properly aligned. They blow air into the coat, replenishing the insulating layer. They roll in the water, working their paws through their fur, checking every inch, ensuring the waterproofing remains intact. If water reaches skin, if the insulation fails, the otter can die from hypothermia within hours. To prevent drifting while sleeping, sea otters wrap themselves in kelp. They locate kelp forests, those towering underwater forests of giant kelp rising from the seafloor, reaching towards sunlight, creating swaying vertical structures that can grow 60 meters tall. The otter wraps a strand of kelp around itself like a sleeping bag, anchoring itself to the forest. Then it floats on its back at the surface, wrapped in kelp, safe from drifting away while it rests. Mothers rest with pups on their chests. The pup, born at sea, never touching land until weaned, rides on its mother's chest while she floats on her back. She grooms it constantly, ensuring its fur develops properly, teaching it by example how to maintain the coat that will keep it alive. The image of a mother otter floating on her back, pup on her chest, both wrapped in kelp, gently rocking in ocean swells, has become iconic, representing perhaps the purest form of peaceful coexistence with the sea. The otter's life revolves around eating, grooming, sleeping, and eating again. They must consume 25% of their body weight daily to fuel their metabolism, their small bodies losing heat rapidly despite the insulating fur, requiring constant energy input to maintain body temperature. They dive to the seafloor, gathering sea urchins, crabs, abalone, mussels. They surface with their catch, often bringing up a rock as well. Floating on their backs, they place the rock on their chests and use it as an anvil, smashing shells open to reach the meat inside. Tool use, problem solving, intelligence applied to the essential task of eating enough to survive. The manatee approaches life with even greater leisure. This herbivorous marine mammal, sometimes called sea cow, moves through coastal waters and rivers at 3 to 5 miles per hour, grazing on seagrass for 6 to 8 hours daily. They are unhurried vegetarians, dedicated to the slow consumption of underwater plants. Manatees sleep submerged. They rest on the bottom or suspend mid-water for periods of 20 minutes, then surface to breathe 1 or 2 breaths, then sink back down to continue resting. Their lungs stretch horizontally along their backs rather than sitting vertically in the chest, as in most mammals. This unusual lung placement provides stable buoyancy, allowing manatees to rest at any depth without constant swimming to maintain position. The horizontal lungs act like built-in flotation devices, keeping the animal balanced and stable. Manatees have no natural predators. Sharks ignore them. Crocodiles coexist with them peacefully. This absence of predation shows in their behavior. They approach boats with curiosity rather than fear. They rest in open water rather than seeking hiding spots. They gather in groups without hierarchy or competition, simply congregating in warm springs during winter, slowly milling about, occasionally interacting but mostly just being present together. They live 60 years, growing to 13 feet long, weighing up to 1,300 pounds. They spend their decades eating, resting, slowly swimming, occasionally mating, existing without urgency in warm tropical waters. The manatee demonstrates what life looks like when predation isn't a constant threat, when food is abundant, when the primary challenge is simply maintaining body temperature in water that sometimes drops below the manatee's tolerance. Their solution: migrate to warm springs in winter, rest in the naturally heated water, wait for warmer weather to return. Patience as seasonal strategy. The giant Pacific octopus provides evidence of something unexpected in an invertebrate: possible dreams. Resting octopuses change colors and textures rapidly. Patterns shift across their skin in waves. Browns, reds, whites, yellows. Smooth skin becomes bumpy. Bumpy skin becomes smooth. The changes occur continuously during rest periods, the patterns flowing across the animal's body like thoughts made visible. Octopuses control their color and texture through their nervous system. Chromatophores, pigment-containing cells, expand and contract under neural control, revealing or concealing different colors. Papillae, small bumps of skin, raise or lower, creating texture. Active octopuses change color for camouflage, matching surrounding rocks or sand. They change color for communication, signaling aggression or attraction to other octopuses. But sleeping octopuses change color without apparent purpose, without external stimuli requiring camouflage or communication. This has led researchers to theorize that the color changes might represent dreaming. The octopus brain might rehearse hunting scenarios, replay recent experiences, process memories, and these internal mental processes manifest visually on the skin. Dreams made visible. Thoughts appearing in real time as shifting patterns of color and texture. Beyond possible dreams, the octopus demonstrates remarkable intelligence. They can unscrew jars to reach food inside. They navigate mazes, learning the correct path after only a few trials. They recognize individual humans, behaving differently toward people who feed them versus people who handle them. They remember solutions to challenges for months, demonstrating long-term memory despite living only 3 to 5 years. Yet they live solitary lives. Adult octopuses occupy dens, caves, crevices, even human artifacts like pipes or bottles, defending these territories from other octopuses. They meet other octopuses only to mate. After mating, males often die within months. Females stop eating while guarding their eggs, starving over months until the eggs hatch. The female uses her siphon to blow water over the eggs, keeping them oxygenated, cleaning them, protecting them from predators. She might guard her eggs for 6 to 10 months, never eating, slowly weakening. When the eggs hatch, releasing thousands of tiny octopuses into the water, the mother dies soon after, her body exhausted beyond recovery. The octopus packages intense intelligence and learning capability into a brief life, then vanishes. Knowledge accumulated by that individual, which jars can be opened, which humans are friendly, which hunting strategies work best, disappears with the individual. Each octopus starts fresh, solving problems anew. There is no multi-generational knowledge transfer, as in dolphins or whales. No cultural transmission, as in grey whales following traditional migration routes. Each generation rediscovers intelligence, uses it for 3 to 5 years, then dies, taking that intelligence with them. This cycle, intelligence arising and disappearing with each generation, makes octopus consciousness particularly poignant. Here is an animal that arguably dreams, that solves complex problems, that learns and remembers, that possibly experiences something we might call subjective experience. Yet it exists briefly, dies young, leaves no legacy except offspring who will start over, discovering intelligence freshly, as though for the first time. These bodies, whale hearts beating twice per minute, dolphins sleeping with half a brain, otters wrapped in kelp, manatees resting on riverbeds, octopuses dreaming in color, represent solutions to the challenge of existing efficiently in the ocean. Each adaptation reduces unnecessary energy expenditure. Each strategy maximizes rest while maintaining essential functions. Breathing, eating, moving, all optimized for minimal effort, maximum sustainability. The bodies are built for stillness because stillness works. In an environment where buoyancy supports weight, where pressure can be used rather than fought, where sound travels farther than light, where food often drifts past rather than requiring pursuit. The optimal strategy isn't constant activity, but efficient rest punctuated by brief, purposeful action. Watch a blue whale cruising at 5 miles per hour, heart beating 6 times per minute, covering thousands of miles annually while expending less energy than a sprinting antelope uses in minutes. Watch a sea otter wrapped in kelp, floating peacefully while waves rock it to sleep. Watch a manatee resting on sandy bottom, suspended by horizontal lungs, breathing every 20 minutes without concern or urgency. These aren't examples of laziness or inefficiency. These are masters of energy conservation, their bodies refined across millions of years to achieve maximum rest while maintaining all necessary life functions. They demonstrate that evolution doesn't always favor speed, aggression, constant activity. Sometimes evolution favors rest. Sometimes natural selection rewards the ability to do nothing beautifully, efficiently, sustainably, and in observing these masters of stillness, in understanding how their bodies achieve such profound calm, we encounter again that lesson the ocean teaches, that life doesn't require constant motion, that rest isn't the absence of living but a sophisticated form of existence, that bodies built for stillness aren't built for passivity, they're built for efficiency, for sustainability, for the long game, where patience outlasts urgency and calm outlives chaos. The blue whale will continue its slow cruising through ocean vastness, heart beating 2 times per minute during deep dives, demonstrating that the largest animal ever to exist thrives on minimal cardiac activity. The octopus will continue changing colors while sleeping, possibly dreaming, its brief, intelligent life burning brightly before extinguishing. The manatee will continue grazing peacefully on seagrass, unbothered and unhurried, living 60 years of gentle existence, and we, observing them, receive the gift of their example, the knowledge that our constant urgency isn't necessary, that rest is a skill worth mastering, that bodies built for stillness carry within them wisdom we desperately need, the wisdom of efficiency, of patience, of allowing the environment to support us, rather than constantly fighting against it. The Greenland shark moves through Arctic waters at less than 1 mile per hour. Less than 1 mile per hour. A pace so slow that a human walking casually would leave the shark behind. This is the slowest swimming shark species ever measured, gliding through water barely above freezing, inhabiting an environment where even movement itself seems to slow down. This glacial pace matches the shark's metabolism, which operates in near-freezing water, temperatures hovering around 0 to 2 degrees Celsius. In such cold, chemical reactions slow dramatically. Enzymes that facilitate cellular processes work sluggishly. The shark's entire body runs on what amounts to slow motion at the molecular level. It grows approximately half an inch per year. Half an inch, a growth rate so gradual that reaching adult size, 24 feet in length, requires centuries, and we do mean centuries. In 2016, researchers published a study that revolutionized our understanding of vertebrate longevity. They performed radiocarbon dating on eye-lens nuclei from 28 Greenland sharks caught by fisheries. The eye-lens nucleus forms when the shark is born and adds no new cells afterward, making it essentially a time capsule of the water chemistry present at birth. By analyzing carbon-14 levels in these nuclei, carbon-14, produced by nuclear testing in the 1950s and 60s, left a distinctive spike in the environment, researchers could estimate when each shark was born The results were extraordinary. The smallest sharks in the study were at least several decades old. Mid-sized sharks were centuries old. The largest specimen, a female measuring 502 centimeters in length, was estimated at 392 years old, with a margin of error suggesting she could be as young as 272 years or as old as 512 years. 500 years. Consider what that means. A Greenland shark swimming through Arctic waters today might have been born before the American Revolution, before the Industrial Revolution, possibly before European contact with the Americas. An animal that has lived continuously through the entire span of modern human history, swimming slowly, patiently, through dark, cold waters, hunting and scavenging, surviving while empires rose and fell, while human population exploded from hundreds of millions to billions, while we transformed the surface world but left the deep Arctic largely untouched. These ancient predators scavenge and hunt with patience incomprehensible to humans. Their diet includes fish, seals, even reindeer and horses that fall through ice, drowned terrestrial animals sinking to the seafloor where Greenland sharks find and consume them. But how does a shark moving at less than 1 mile per hour catch active prey like seals? The answer appears to be by hunting sleeping seals. Researchers examining stomach contents found sleeping seals, identifiable because they were whole and undamaged, apparently swallowed without struggle. This suggests Greenland sharks approach sleeping seals on the seafloor slowly enough to avoid triggering escape responses. The seal sleeps. The shark approaches over minutes, perhaps hours, moving so gradually that the seal's nervous system doesn't register threat. When the shark gets close enough, it strikes, not through speed but through sudden proximity, opening its mouth and creating suction that pulls the seal in. The shark's eyes host a specialized parasite, a copepod that attaches to the cornea and dangles forward like a lure. Earlier theories suggested this dangling copepod might attract prey toward the shark's mouth, though recent research questions whether the parasite significantly helps with hunting or whether it simply reduces the shark's vision without providing benefits. Regardless of the parasite's function, one fact remains clear. The Greenland shark succeeds despite being nearly blind, despite moving slower than humans walk, despite inhabiting waters where food is scarce and encounters with prey are rare. The shark continues its slow patrol through dark Arctic waters, unhurried, patient beyond measure, scavenging and hunting with methods refined over hundreds of individual years. This particular shark, remembering hunting strategies that worked decades ago, learning slowly, adapting gradually, accumulating centuries of experience and millions of evolutionary years behind that. The species itself proving that extreme patience can be a viable survival strategy even for apex predators. The great white shark contrasts sharply in method but maintains the same underlying patience. These legendary predators can swim at 25 miles per hour in short bursts, explosive acceleration used during the final approach to prey. But they spend most of their time cruising slowly at 2 to 3 miles per hour, conserving energy, covering vast distances, while burning minimal calories. Great whites are ectothermic, their body temperature influenced by environmental temperature, but they maintain elevated core temperatures through a specialized adaptation called countercurrent heat exchange. In their circulatory system, warm arterial blood flowing from the core toward extremities passes very close to cold venous blood returning from extremities toward the core. Heat transfers from warm blood to cold blood. The arterial blood cools slightly before reaching extremities. The venous blood warms significantly before returning to the core. The result: core body temperature remains up to 14 degrees Celsius above surrounding water temperature. This warmth enables higher sustained swimming speeds and more powerful muscle contractions than truly cold-blooded sharks can achieve. But it also requires more food to fuel the metabolic furnace. A great white must hunt successfully enough to maintain its elevated temperature, to power its cruising patrols, to support growth and reproduction. The shark cannot afford to waste energy on unsuccessful hunts. Efficiency becomes paramount. Hunting happens through ambush. Great whites patrol along seal colonies, places like the waters off Seal Island in South Africa, Guadalupe Island off Mexico, the Farallon Islands outside San Francisco Bay. They swim deep, typically 30 to 40 meters down, where their dark backs blend with dark water below. From above, looking down, predators struggle to see the shark against the darkness of depth. The shark watches the surface. When a seal swims overhead, backlit by sunlight, its silhouette stands out clearly. The shark accelerates upward, timing the ascent to arrive at maximum speed. Just as it reaches the prey, the shark strikes from below. The attack generates enough momentum that shark and seal sometimes breach completely out of the water, several tons of shark launching into air, mouth opened wide, multiple rows of serrated teeth closing on impact. If successful, if the shark's teeth grip the seal properly, the shark releases. It doesn't immediately consume its prey. Instead, it waits. The seal, bleeding from massive wounds, weakens rapidly. After some time, minutes, perhaps longer, the shark approaches again and begins feeding. This strategy reduces risk. A healthy seal can fight, can injure the shark with bites or scratches. A weakened seal offers no resistance. Patience improves safety. If unsuccessful, if the seal evades the attack, if the shark misses, the shark doesn't chase frantically. It returns to deep water, resumes patient waiting. Sometimes weeks pass between successful hunts. The shark's slow metabolism and elevated but not extreme body temperature allow it to survive extended periods without food. When opportunity arises, it strikes decisively. Between opportunities, it waits. The great hammerhead shark demonstrates how body shape itself becomes hunting strategy. The bizarre hammer-shaped head, called a cephalofoil, spans up to 6 feet wide on large individuals. This isn't evolutionary whimsy. The expanded head creates a sensory platform studded with electroreceptors called ampullae of Lorenzini. These jelly-filled pores detect electrical fields generated by muscle, contractions and nervous systems of prey animals. Every living creature produces electrical signals, nerve impulses, muscle contractions, heartbeats, creating electromagnetic fields in the surrounding water. The hammerhead's wide head, covered in electroreceptors, scans these fields like a metal detector sweeping across beach sand. The shark swims slowly along seafloor, sweeping its head back and forth, hunting stingrays buried under sand. The ray hides motionless, covered by sediment invisible to sight. But its heartbeat continues. Its respiratory muscles contract, pumping water over gills. These muscle contractions generate tiny electrical fields that penetrate the sand. The hammerhead detects them. When electrical signals reveal hidden prey, the hammerhead uses its head as a tool. It pins the ray to the bottom, pressing down with the cephalofoil, holding the ray in place while maneuvering its body to achieve biting position. The ray's barbed tail whips defensively, sometimes striking the shark. Examination of hammerhead jaws often reveals multiple stingray barbs embedded in the mouth and face, testament to the danger of this hunting strategy. Yet, the hammerhead persists. Evolution has favored increasing tolerance to ray venom while maintaining preference for these well-defended prey. The wide head provides sensory advantage that apparently outweighs the risk of envenomation. The shark hunts patiently, systematically scanning seafloor, striking when electrical signals reveal prey. Accepting injury as cost of successful predation, the manta ray, related to stingrays but utterly different in lifestyle, abandoned hunting entirely. These graceful giants, growing to 23 feet across from wingtip to wingtip, feed exclusively by filtering plankton from water. They surrendered the predatory lifestyle shared by most of their relatives in favor of peaceful filtering, becoming oceanic grazers rather than hunters. Manta rays swim with slow, powerful wing-like pectoral fins that flap rather than undulate. The motion resembles a bird in flight, more than a typical fish's swimming. They cruise at 3 to 4 miles per hour during normal swimming, capable of accelerating to 9 miles per hour when necessary but rarely bothering. The pace remains leisurely, unhurried, sustainable across hours of continuous swimming. Their mouths stretch wide, up to 4 feet across in large individuals. As they swim, water funnels into this enormous mouth. Inside, gill rakers, comb-like structures, filter zooplankton from the water while allowing water to exit through gill slits. The manta might swim in loops through productive water, passing through the same patch of plankton repeatedly, or swim with mouth open continuously for hours, straining food from currents without conscious thought. The filtering happening automatically as water flows through their system. The manta ray eats some of the ocean's smallest prey, zooplankton, tiny shrimp-like creatures, fish larvae, while itself being one of the ocean's largest fish. This inversion, massive predator eating tiny prey, appears in the ocean's largest creatures repeatedly. Blue whales eat krill. Whale sharks eat plankton. Manta rays eat zooplankton. Size enables long life, broad-ranging, reduced predation, but supporting that size requires enormous energy input, achievable only through filtering vast quantities of nutrient-rich water. Manta rays gather at cleaning stations, specific coral formations where cleaner fish wait to remove parasites. The ray approaches slowly, identifies the cleaning station, and hovers. Sometimes it tilts its body vertical, head up or head down. It extends its cephalic fins, horn-like projections on either side of its mouth, allowing cleaners access to every surface. The cleaning may last 10 to 15 minutes. Dozens of cleaner fish pick parasites from skin, gills, mouth. They enter the ray's gill chambers, swimming inside to clean internal surfaces. The ray remains motionless, patient, allowing this intimate access to creatures small enough to swallow accidentally. The relationship benefits both species. Rays gain parasite removal. Cleaners gain nutrition, and the interactions display recognizable ritual. Rays queue up, waiting their turn at popular stations. They return to the same locations repeatedly across months and years. Individual rays recognize specific cleaning stations, suggesting memory and sight fidelity beyond simple instinct. The cleaning stations become social centers, meeting places where rays gather not just for cleaning, but perhaps for social contact, for the company of others of their kind in an otherwise vast and often solitary ocean. The whale shark surpasses the manta ray in size, reaching lengths of 60 feet and weights exceeding 20 tons, becoming the largest fish in the ocean. Not the largest animal, whales are larger, but the largest fish, the largest creature with gills, scales, and a cartilaginous skeleton. Like mantas, whale sharks feed by filtering. They swim slowly through plankton. Clouds with mouths agape, mouths measuring up to 5 feet wide, processing over 1,500 gallons of water per hour through gill rakers that strain out organisms as small as 0.5 millimeter. They feed continuously during plankton blooms, which might last hours or days, accumulating nutrition enough to sustain them through leaner times. Whale sharks can actively suck water and prey into their mouths, creating enough vacuum force to pull small fish from several feet away. They sometimes position themselves vertically in the water column, head up, mouth at the surface, and bob up and down, gulping water and prey with each upward movement. The strategy concentrates plankton near the surface where feeding efficiency improves despite their massive size and impressive migrations. Individuals, tagged with satellite transmitters, have traveled over 7,500 miles. Whale sharks display gentle, almost curious behavior around humans. Divers swim alongside them, sometimes for hours. The shark maintains its slow, steady pace, mouth opening and closing rhythmically, filtering continuously, unbothered by human company. They don't flee or attack. They simply continue whatever they were doing, tolerating proximity with remarkable patience. Their spotted patterns, unique to each individual like fingerprints, allow researchers to identify and track individuals across decades. A whale shark photographed off Mexico one year might be photographed off the Philippines 3 years later. The same distinctive pattern of spots confirms identity across thousands of miles and years of time. Long-term tracking reveals that whale sharks may live 70 to 100 years, spending their long lives drifting through oceans, feeding when plankton blooms occur, traveling between productive areas, existing in patient progression through blue vastness. The sea star represents hunting, reduced to absolute simplicity. To patients so extreme, it seems barely distinguishable from stillness. Most sea star species move at speeds measured in centimeters per minute, 6 to 10 centimeters per minute for common species. At 10 centimeters per minute, a sea star travels 6 meters per hour. At that pace, crossing a football field requires 17 hours. This isn't travel. This is persistence measured in glacial time. The sea star moves using hundreds of tube feet on its underside. Each tube foot extends and attaches to substrate using suction. Then it contracts, pulling the sea star forward minutely. The foot releases, extends, attaches again slightly forward. Hundreds of feet coordinate this motion in slow waves that ripple along each arm. The overall effect produces forward movement so gradual it's difficult to perceive without time-lapse photography. Sea stars hunt bivalves, clams, mussels, oysters, prey that seem well defended behind thick shells capable of closing tightly. The sea star approaches slowly, moving at its characteristic centimeters per minute pace. It positions itself atop the bivalve. It grips the shell with tube feet on multiple arms, distributing grip points around the shell's edge. Then it begins pulling. The pull isn't violent. It's steady, constant. The sea star maintains tension on the shell continuously, pulling with equal force from multiple directions. The bivalve's muscles, the adductor muscles that hold the shell closed, must maintain constant contraction to resist. The sea star's tube feet work in shifts. Some relax while others pull. The overall force remains constant, but the bivalve's muscles cannot relax. They must sustain maximum contraction indefinitely. Hours pass. The bivalve's muscles begin to fatigue. The shell gaps open slightly. The opening might be only a few millimeters, barely visible, but it's enough. The sea star extrudes its stomach through its mouth, inserts the stomach into the small opening, and begins digesting the bivalve externally. Digestive enzymes liquefy the bivalve's tissue. The stomach absorbs the liquefied nutrients. When feeding is complete, the sea star pulls its stomach back inside its body and moves on, leaving behind an empty shell. This hunting strategy succeeds through patience alone. The sea star possesses no speed, no strength beyond what it can sustain indefinitely, but it can maintain pressure for hours, even days if necessary. Eventually, every muscle fatigues. The sea star simply waits for that moment, prepared to continue waiting as long as required. If damaged, if an arm breaks off, if a predator bites the sea star, regeneration begins slowly. A lost arm regrows over months. Visible progress requires weeks, but the regeneration continues relentlessly. Cells dividing and specializing, new structures forming until wholeness returns. In some species, a severed arm can regenerate an entire new body if it retains part of the central disc, essentially cloning the original sea star through patient regrowth. The sea star's nervous system lacks centralization, no brain coordinates movements. Instead, a nerve ring circles the central disc with nerve cords extending into each arm. The hundreds of tube feet coordinate through distributed processing, each foot responding to local conditions while somehow maintaining overall coordination. The regeneration proceeds without conscious oversight. The animal hunts, moves, survives through consensus rather than command, through distributed awareness rather than central control. These hunters, the Greenland shark living centuries, the great white shark waiting weeks between hunts, the hammerhead scanning seafloor systematically, the manta ray filtering peacefully for hours, the whale shark crossing ocean basins to find plankton blooms, the sea star pulling at shells until muscles fatigue, demonstrate that hunting doesn't require aggression or urgency. In terrestrial environments, predation often looks like cheetahs sprinting, lions charging, wolves chasing. Speed and power, overwhelming force. The hunt condensed into moments of explosive action. But the ocean offers different options. Buoyancy removes the energy cost of standing or walking. Water's density slows movement, but allows creatures to wait suspended, burning minimal calories while watching for opportunity. Food often concentrates in predictable locations, cleaning stations, plankton blooms, seal colonies, removing the need to search vast territories. In this environment, patience becomes viable hunting strategy. The Greenland shark can afford to move at less than 1 mile per hour because prey must eventually sleep, and sleeping prey cannot flee slowly approaching predators. The great white can afford to wait weeks between hunts because its elevated but not extreme metabolism allows survival on infrequent meals. The whale shark can afford to migrate thousands of miles because plankton blooms, when found, provide abundant food worth the travel cost. Watch a manta ray swimming in slow loops through plankton clouds, mouth open, filtering continuously, gathering nutrition through patient accumulation rather than dramatic strikes. Watch a sea star gripping a clam, maintaining pressure hour after hour, succeeding through persistence rather than power. These are masters of the long game, their hunting strategies refined across millions of years to achieve success through waiting rather than chasing, through patience rather than speed, and in their patience, they teach us something essential about existence itself. That success doesn't always come through aggressive action. That waiting can be strategy rather than passivity. That time, given enough of it, accomplishes what force cannot. That in a universe often appearing to favor the quick and powerful, there exist equally valid paths to survival through stillness, through patience, through the quiet confidence of knowing that eventually opportunity comes to those prepared to wait. The Greenland shark will continue its centuries-long patrol through Arctic waters, moving slower than humans walk, hunting sleeping seals, embodying patience at scales we can barely comprehend. The whale shark will continue filtering plankton, traveling oceans, living decades while maintaining that same gentle, unhurried pace. The sea star will continue pulling at shells, maintaining pressure hour after hour, succeeding through persistence alone, and we, watching these hunters who wait, receive their lesson, that the ocean teaches patience not just as virtue, but as viable strategy, that hunting itself can be practiced peacefully when time becomes ally rather than enemy, that in the art of waiting, truly waiting, without anxiety or urgency, there exists a form of power available to those patient enough to discover it. The humpback whale song represents the most complex vocalization produced by any non-human animal. Not simple calls or warning sounds, but structured compositions organized into hierarchical patterns that resemble, in their complexity, human language and human music. Males sing during breeding season. Each song lasts 10 to 20 minutes, then repeats. The repetition can continue for hours, the same song over and over, broadcast into the ocean. But calling it the same song oversimplifies what's actually happening. The songs contain themes made up of phrases, made up of individual units, organized hierarchically like nested boxes, each level contributing to the overall structure. A unit might be a single sound, a groan, a cry, a series of pulses. Multiple units combine into a phrase. Multiple phrases combine into a theme. Multiple themes arranged in specific order create the complete song. The complexity rivals human music in structural sophistication. The whale isn't simply making noise. It's performing a composition, and here's what makes it extraordinary. All males in a population sing essentially the same song. Humpback whales in the North Pacific sing one song. Humpback whales in the North Atlantic sing a different song. But within each population, the males sing the same composition, the same themes, the same phrases, generally the same unit arrangements. Yet the song evolves. Slowly, across months, phrases change. A grunt becomes longer. A cry's pitch shifts slightly. New themes emerge. Old ones disappear. By the next breeding season, the song has transformed into a different composition, though still recognizably related to the previous year's version. Year after year, the song continues changing, evolving, developing new variations while maintaining some core characteristics. How do whales learn these changes? How does the entire population adopt modifications without any central teaching authority, without any way to broadcast instructions, without notation or recording? The question remains largely mysterious. Somehow cultural transmission occurs, whales learning from other whales, innovations spreading through the population, changes adopted collectively, creating what amounts to evolving cultural traditions maintained purely through sound and memory. The songs travel extraordinary distances. Low-frequency components, sounds below 100 Hz, below the lowest notes audible to humans, propagate through the ocean for hundreds of miles before fading. These deep sounds travel farthest because they suffer less absorption by water than higher frequencies. The ocean becomes more transparent to low-frequency sound, allowing it to spread across vast distances, and there's more. At depths of 600 to 1200 meters, a zone exists where sound waves behave unusually. Called the Deep Sound Channel, or SOFAR channel, sound fixing and ranging, this depth experiences a specific combination of pressure and temperature that creates a waveguide for sound. Sound waves entering this channel refract upward and downward, but not outward, trapped in a horizontal layer that allows transmission across entire ocean basins. A whale vocalization entering the SOFAR channel can theoretically reach another whale 5,000 miles away. 5,000 miles. The distance from California to Japan, from Brazil to Africa, from Madagascar to Australia. A whale song, produced by vibrations in the animal's larynx, traveling across continents of ocean, connecting individuals separated by distances that would take months to swim. Whether whales intentionally use the SOFAR channel remains unknown. But their songs reach throughout ocean regions regardless, creating acoustic connections between individuals spread across vast territories. The ocean becomes laced with whale songs, overlapping compositions from different singers, different populations, different species, all broadcasting simultaneously, filling the water with structured sound. The sperm whale speaks a different acoustic language. Its clicks serve multiple purposes, each adapted to different social and hunting needs. Echolocation clicks, used for hunting, burst out at rates of 1 to 2 per second while the whale searches. The clicks travel outward, strike objects, squid, fish, the seafloor, and echo back. The whale's massive head, filled with spermaceti oil, appears to focus these clicks into directional beams, allowing the whale to see through sound in darkness, where eyes provide no information. When prey is located, the clicking accelerates dramatically. The rate increases to a creaking sound, exceeding 200 clicks per second. So rapid, the individual clicks blur together into continuous sound. This rapid clicking provides detailed acoustic images as the whale closes in, analogous to how bats increase echolocation rate when approaching insects. The whale builds a sound picture of its target, updating that picture hundreds of times per second, using acoustic information to guide the final approach and strike. Social clicks, called codas, follow rhythmic patterns. 3 clicks in quick succession, 5 clicks with specific timing, 7 clicks arranged distinctly. These codas vary by clan, suggesting dialects or perhaps even names. Sperm whales live in matrilineal groups, 10 to 20 females with their young, led by the oldest females, staying together for life. Males leave these family groups at sexual maturity, traveling alone or in bachelor groups. The codas may identify individuals or family groups. They might announce, "This is me, this is us. We belong to this clan." The patterns maintain social bonds across dark depths where vision provides no information, where physical proximity might be dangerous, given the whale's massive size, where sound becomes the primary medium for connection. Sperm whale clicks reach 200 to 236 decibels, louder than jet engines at close range, louder than any sound humans can safely experience. Some researchers theorize the clicks might stun prey through acoustic force, creating shockwaves powerful enough to disorient or kill giant squid. The evidence remains inconclusive, but the volume is undeniable, measurable, almost incomprehensible in its intensity. Yet despite producing these extraordinarily loud clicks, the clicking fills the ocean not with cacophony, but with rhythm. Multiple whales clicking simultaneously create overlapping patterns that pulse through the water column. Hydrophones lowered into deep water record these exchanges, translating them into audio humans can perceive. The recordings reveal constant conversation, creaks and codas, regular clicks and rapid bursts, a three-dimensional spatial audio environment where sperm whales communicate through darkness using sound alone. If whale songs demonstrate acoustic complexity at large scales, snapping shrimp demonstrate that small creatures can be among the loudest. These shrimp, typically 1 to 2 inches long, small enough to fit in a human palm, possess one enlarged claw that snaps shut with incredible speed. The claw features a socket on one half and a plunger on the other. Muscles cock the plunger back. Then in a burst of muscular contraction, the plunger releases. The claw snaps shut so rapidly that water cannot flow quickly enough to fill the closing space. The result? A cavitation bubble. Water pressure drops so suddenly that a vacuum bubble forms. The bubble exists for less than 1 millisecond before water pressure collapses it. And when the bubble collapses, it produces a sound reaching 210 decibels and generates light through sonoluminescence. The bubble collapse concentrates so much energy in such a small space that it creates a flash of light lasting less than 10 billionths of a second. The bubble interior heats to over 5,000 degrees Celsius, nearly as hot as the sun's surface, producing a brief flash of light from pure kinetic energy. From the violence of collapsing water, individual snaps last milliseconds. But snapping shrimp don't live individually. They form colonies containing thousands or millions of individuals. In shallow tropical and subtropical waters, these colonies dominate the acoustic environment, all snapping constantly, thousands of snaps per second, millions of snaps per hour. The combined sound creates crackling soundscapes that interfere with sonar and submarine communication, that dominate underwater recordings, that characterize healthy reef environments. To a hydrophone, a healthy reef sounds like cooking bacon. The continuous crackle of countless shrimp snapping provides an acoustic signature of reef health. Scientists now assess coral ecosystems by recording their sound. Loud crackling indicates vibrant populations, many shrimp, abundant life, healthy reef structures. Silence suggests degradation, few shrimp, reduced populations. Damaged or dead reef, the snapping shrimp colonies create perhaps the ocean's most consistent soundscape, continuous, rhythmic, omnipresent in shallow tropical waters, a crackling backdrop against which all other sounds occur. Not beautiful in any traditional sense, but constant, reliable, the acoustic indicator of reef vitality. Fish produce sounds through various mechanisms. Though most fish sounds remain unknown to casual observers who think of the ocean as silent. Some fish vibrate their swim bladders, gas-filled organs used primarily for buoyancy control. Surrounding muscles contract rhythmically, causing the bladder to vibrate like a drum. The resulting sounds range from grunts to drums to low-frequency hums, depending on vibration rate and bladder size. The swim bladder amplifies these sounds, acting as resonance chamber that projects vibrations into surrounding water. Others grind pharyngeal teeth in their throats, producing raspy sounds. Triggerfish create pulses by vibrating tendons against swim bladder walls. Various species have evolved different mechanisms, but the function remains similar, producing sound for communication, for territorial defense, for courtship, for maintaining group cohesion. The The oyster toadfish produces foghorn-like calls during courtship. Males establish territories and call to attract females. The call, a sustained foghorn blast, results from muscles surrounding the swim bladder contracting at specific rates. The male calls continuously for up to an hour, broadcasting its presence across reef habitat. The foghorn repeats, call, silence, creating a pattern that females recognize and approach. Males guard eggs after mating, defending the nest site against predators and rivals. They return to the same nest site year after year, establishing long-term territories that they defend season after season. The calling announces not just current reproductive status, but long-term residency, ownership of prime territory worth defending. The midshipman fish, named for bioluminescent spots resembling naval uniform buttons arranged in rows along its body, takes vocal endurance even further. Males create nests under rocks in intertidal zones, then hum continuously during breeding season, not calling intermittently, but sustaining single notes for over an hour without pause. The hum frequency sits around 100 Hz, low enough to carry well through water, audible above water to nearby residents. In areas with high midshipman populations, the combined humming from multiple males creates loud droning that reverberates through coastal neighborhoods, sometimes prompting noise complaints from residents who can't identify the source. The humming requires extreme muscle control. Superfast muscles capable of contracting 200 times per second, vibrate the swim bladder at frequencies that create the humming tone. Maintaining these rapid contractions for hours nightly across weeks demands extraordinary muscular endurance. The male invests tremendous energy in calling, waiting for females to arrive, demonstrating that even fish can practice endurance courtship, requiring patience sustained across long time scales. Females attracted to the humming locate nests and lay eggs. Males guard eggs until hatching, then begin calling again the next season. The cycle repeats annually, the humming filling coastal waters each breeding season, an acoustic signature of intertidal spawning zones. Coral reefs themselves produce complex soundscapes assembled from multiple sources. Waves breaking against reef structures create one layer, crashes, hisses, the rumble of water moving over calcium carbonate formations. Snapping shrimp add their crackling. Fish calls, grunts, whistles, pops, drumming add melodic and percussive elements. The combined effect creates a distinct acoustic signature unique to healthy reefs. The soundscape changes with time of day. More activity at dawn and dusk, quieter during midday and midnight. It changes with season. Breeding periods bring increased calling. Larval settlement brings different activity patterns. But healthy reefs maintain consistent baseline sound levels that indicate thriving ecosystems. Juvenile fish use these soundscapes for navigation. Larvae drifting in open ocean, tiny, transparent, seemingly helpless, detect reef sounds from significant distances. Studies tracking larval fish show them swimming toward reef soundscapes, using acoustic cues to locate suitable settlement habitat. The sound provides a beacon, guiding larvae from open ocean darkness toward the complex structures that will become their home. This creates a positive feedback loop. Healthy reefs produce loud soundscapes. Loud soundscapes attract larval settlement. Settlement increases reef populations. Increased populations produce more sound. The loop reinforces itself. Healthy reefs becoming acoustic beacons that draw larvae towards stability, creating the next generation that will maintain the soundscape. Conversely, damaged reefs fall silent. Without snapping shrimp, without abundant fish, without the activity that generates sound, degraded reefs become acoustically quiet. Larvae drifting past quiet reefs often don't settle, instead continuing to drift, searching for the acoustic signatures that indicate suitable habitat. Silence becomes a death sentence, quiet reefs failing to attract the new. Generations needed for recovery. The Antarctic Weddell seal vocalizes beneath. Sea ice in an environment that seems impossibly harsh, yet supports sophisticated acoustic communication. These seals produce trills, whistles, and chirps that carry through the water column. Males create underwater territories during breeding season, defending areas beneath ice where females gather. The vocalizations announce presence. This space is occupied. Warn competitors. Don't approach. And attract females. I'm available. I'm strong enough to hold territory. The sounds carry well under ice, where the ice ceiling above creates natural reverb, extending call duration and enhancing territorial coverage. Recordings of Weddell seal vocalizations reveal otherworldly quality, rising and falling tones, warbling trills, sounds seemingly synthetic but produced entirely by biological mechanisms. The seals modulate their calls with precision, creating patterns that other seals recognize individually. Personal acoustic signatures, identifying specific males, allowing females to distinguish between potential mates based on call characteristics. The acoustic environment beneath Antarctic ice becomes an amphitheater. Seal voices echo off the ice ceiling, reflect off the seafloor, bounce between ice walls in channels and cracks. Sound travels in 3 dimensions, filling the space with overlapping calls that create complex acoustic landscapes. Multiple males calling simultaneously from different territories generate spatial audio environments where position correlates with sound source, allowing listeners to locate callers through acoustic triangulation. These sounds, whale songs evolving across seasons, sperm whale clicks stunning prey, snapping shrimp creating cavitation bubbles, fish humming for hours, reef soundscapes guiding larvae, seal trills echoing under ice, fill the ocean with acoustic information. The ocean isn't silent. It's loud, continuously, variably, complexly loud, filled with structured sound carrying meaning, maintaining connections, facilitating survival. Sound travels 4 times faster through water than through air, 1,500 meters per second compared to 340 meters per second. Sound also travels farther, much farther, before dissipating. These physical properties make the ocean an acoustic environment first, a visual environment second. Where light penetrates 200 meters at most, sound travels thousands of miles. Where sight reveals only nearby objects, sound reveals distant creatures, approaching predators. Available mates separated by vast distances. In this acoustic ocean, creatures evolved to use sound for communication. For navigation, for hunting, for courtship, for maintaining social bonds. They produce sounds through mechanisms we're still working to fully understand. Swim bladder vibrations, muscle contractions, cavitation bubbles, laryngeal vibrations. They detect sounds through mechanisms equally diverse. Pressure-sensitive lateral lines, specialized hearing structures, whole-body vibration detection. The result? An ocean filled with sound. Not random noise, but structured information. Songs that evolve. Coders that identify clans. Snaps that indicate reef health. Hums that attract mates. Soundscapes that guide larvae. An acoustic dimension as rich and complex as the visual dimension we rely on terrestrially. Accessible to creatures whose evolution occurred in an environment where sound matters more than sight. When we lower hydrophones into the ocean and listen, we hear complexity that surprises us. We expect silence. We find conversation, continuous, variable, meaningful conversation occurring in languages we barely understand, using mechanisms we're still discovering, maintaining social structures and ecological relationships that depend fundamentally on sound. The humpback whale continues singing its evolving composition. The song changing slowly across months, spreading through populations, connecting individuals across ocean basins. The sperm whale continues clicking in darkness, using sound to see, to speak, to maintain family bonds across depths where light never reaches. The snapping shrimp continue creating their crackling soundtrack, billions of tiny explosions announcing reef vitality. And we, listening to these sounds, discover yet another dimension of ocean tranquility. The sounds aren't chaotic. They're structured, rhythmic, purposeful. Whale songs follow patterns. Reef soundscapes pulse with predictable daily rhythms. The ocean speaks not in random noise, but in ordered sound. in acoustic patterns as reliable as visual patterns, in soundscapes that once understood, reveal as much information as landscapes reveal to eyes. This acoustic richness offers us something unexpected. When we listen to ocean sounds, recordings of whale songs, reef soundscapes, the rhythmic clicking of dolphins, our nervous systems respond. Heart rates slow. Brain waves shift toward patterns associated with relaxation. The sounds trigger responses that suggest deep recognition. Perhaps evolutionary familiarity with acoustic environments our ancestors knew. Perhaps simple neurological reactions to rhythmic sound at frequencies that resonate with human physiology. Whatever the mechanism, the effect remains consistent. Ocean sounds calm us, not through silence, but through structured sound that follows patterns our brains find meaningful, rhythmic, soothing. We discover that peace doesn't require absence of sound. It requires sound that follows patterns, rhythms we can predict, frequencies that don't jar, acoustic landscapes that change gradually rather than abruptly. The ocean's acoustic dimension demonstrates this perfectly, constantly producing sound, yet creating overall soundscapes that mammals, including humans, find deeply calming. The sounds beneath the surface teach us that tranquility and richness aren't opposites, that calm can coexist with complexity, that silence isn't required for peace when sound itself becomes structured, rhythmic, purposeful, when sound becomes music, conversation, connection, rather than mere noise. The clownfish swims among tentacles that would kill almost any other creature. Sea anemones possess nematocysts, specialized cells lining their tentacles that fire harpoon-like structures loaded with venom when triggered by contact. These microscopic weapons discharge in less than a millisecond, penetrating skin, injecting toxins that paralyze prey, causing intense pain in anything large enough to experience pain. Yet the clownfish moves through this deadly garden unbothered. It brushes against tentacles deliberately. It rests between them. Sometimes it appears to dance, weaving through the swaying arms, coming into contact repeatedly without triggering the stinging cells or, more remarkably, triggering them but remaining immune to the venom. How? Multiple theories attempt to explain this immunity. The clownfish produces specialized mucus coating its body. This mucus may contain chemical compounds that mimic the anemone's own mucus, preventing the nematocysts from recognizing the fish as foreign. The anemone's stinging cells evolved not to fire against the anemone itself. Self-stinging would be self-destructive. If the clownfish's mucus chemically resembles the anemone's, the nematocysts might treat the fish as part of the anemone, declining to fire. Alternatively, the clownfish may acclimate gradually. Young clownfish approaching an anemone for the first time brush against tentacles gently, briefly, building tolerance through repeated exposure. The mucus composition might adjust over time, incorporating compounds from the anemone itself, creating chemical camouflage through environmental adaptation rather than genetic programming. Regardless of mechanism, the result creates one of the ocean's most elegant partnerships. The clownfish gains protection from predators that won't approach the anemone's stinging tentacles. Predatory fish, hungry and capable, see the clownfish, but won't risk the anemone's venom to catch it. The clownfish lives surrounded by deadly weapons that protect without harming it. The perfect refuge. The anemone gains benefits too. The clownfish produces waste, ammonia and other compounds that in the enclosed space within the anemone's tentacles become nutrients the anemone can absorb. Food scraps from the clownfish's meals drift down into the anemone's oral disc, providing additional nutrition. The clownfish chases away butterfly fish, predators that eat anemones, defending its host aggressively from creatures that might damage or kill it. In the wild, certain clownfish species associate exclusively with certain anemone species. Amphiprion ocellaris, the common clownfish, lives with Heteractis magnifica, the magnificent sea anemone, or with Stichodactyla gigantea, the giant carpet anemone. Other clownfish species choose other anemone species. The partnerships follow patterns suggesting co-evolution, millions of years during which fish and anemone adapted to each other, each species refining the relationship, creating dependencies that benefit both. The relationship can last the lifetime of both organisms. Anemones live decades, some species potentially living centuries, though tracking individual anemones across such timescales proves difficult. Clownfish live 6 to 10 years in the wild. A family group of clownfish, typically one breeding pair and several non-breeding juveniles, can occupy the same anemone for the entire lives of the adult fish, with juvenile fish maturing to replace adults that die. Maintaining occupancy across decades, this creates household units. The anemone becomes home. The clownfish family lives within it, defends it, depends on it completely. The anemone provides shelter, the clownfish provide nutrients and defense. Neither thrives as well when separated. Both flourish together, creating a micro-ecosystem within the larger reef. A partnership so integrated that defining where one organism's needs end and the other's begin becomes nearly impossible. The cleaner wrasse built its entire lifestyle around service to others. These small, colorful fish, typically 4 to 6 inches long, bright blue with horizontal black stripes, establish cleaning stations at specific locations on reefs. The stations become known. Larger fish visit them regularly, sometimes traveling considerable distances, sometimes waiting in queues when stations become busy. When a client fish approaches, the cleaner performs an invitation dance. It swims up and down rapidly, displaying its distinctive coloration, signaling availability. The client fish signals acceptance by stopping its swimming, sometimes tilting its body, sometimes opening its mouth or flaring its gill covers. The postures communicate, "I'm ready for cleaning. I won't eat you. Please proceed." The cleaner then methodically inspects the client's body. It picks parasites from skin, removing copepods, isopods, and other external parasites that plague fish. It removes dead or infected tissue from wounds. It enters the mouth, swimming between teeth, checking for food particles or parasites. It enters the gill chambers, the most vulnerable parts of the client's anatomy, swimming inside to clean surfaces where parasites often hide. The client fish remains motionless during this process. A grouper might hover mid-water, holding an awkward posture for 10 or 15 minutes, allowing thorough cleaning. A shark might rest on the reef, gills pumping slowly, permitting the tiny cleaner access to its mouth and gills, despite being capable of swallowing the cleaner in one bite. The stillness demonstrates trust, vulnerability accepted temporarily, because cleaning benefits outweigh risks. The relationship involves genuine recognition and decision-making on both sides. Client fish remember locations of cleaning stations. They return to the same stations repeatedly across months and years. They prefer certain individual cleaners over others. At popular stations, clients queue, waiting for their turn with preferred cleaners rather than accepting immediate service from less favored individuals. This suggests quality assessment. Some cleaners provide better service than others, and clients recognize this, making choices based on past experiences. Cleaners remember individual clients too. They treat familiar fish differently from strangers. Regulars receive immediate service. New visitors might be approached more cautiously, inspected more carefully. The cleaner assesses the client before committing to service, determining whether the interaction seems safe, whether the client appears likely to reciprocate cooperation. Experiments reveal even more sophisticated behavior. Cleaners adjust their service quality based on audience. When other potential clients watch, when fish wait in queue, observing the cleaning interaction, cleaners provide better service. They spend more time cleaning, remove more parasites, offer more thorough inspections. When no audience watches, service quality sometimes decreases. The cleaner might bite the client, removing not just parasites but healthy mucus or tissue, benefiting at the client's expense. This suggests reputation management. Cleaners that provide good service when watched maintain reputations that attract clients. Cleaners that cheat risk losing clients to competitors. The system creates pressure for honest cooperation, enforced not through punishment but through client choice, through the market dynamics of multiple cleaners competing for limited clients. The Cleaner Rasa demonstrates that even fish can practice hospitality, building careers on trustworthiness maintained across repeated interactions. The cleaning stations become social institutions, places where cooperation gets rewarded, where both parties benefit, where the interaction itself becomes ritualized through evolutionary time until it follows predictable patterns that both cleaner and client recognize and enact. The remora and shark partnership follows a different model, one-sided benefit tolerated rather than mutual cooperation. Remoras possess a modified dorsal fin transformed into a suction disc on top of their heads. The disc consists of parallel ridges that create vacuum when pressed against surfaces. The remora attaches to sharks, rays, whales, or sea turtles, hitchhiking through the ocean while its host swims, attached to its host. The remora feeds on scraps from the host's meals, bits of flesh torn loose during predation, floating fragments that would otherwise disperse. It also feeds on parasites on the host's skin, providing some cleaning service, though far less systematically than Cleaner Rasa. The remora gains transportation and food. The host gains minimal parasite removal, but must carry the remora's weight and drag. Yet hosts rarely try to remove remoras. Sharks don't rub against reefs to dislodge them. Whales don't breach repeatedly to shake them off. Manta rays sometimes carry a dozen remoras simultaneously, several on the belly, some on the back, others on the wing edges, yet continue swimming at their usual pace. Apparently unbothered by the passengers, large manta rays demonstrate something interesting. When visiting cleaning stations, remoras detach temporarily. The ray arrives, hovers for cleaning, and the remoras release, swimming free during the cleaning session. When the ray departs, remoras reattach, resuming their hitchhiking. This suggests coordination beyond simple parasitism. The remoras recognize cleaning sessions, adjust their attachment behavior accordingly, allowing the ray to receive proper cleaning before reattaching for continued transport. The behavior implies that remoras treat hosts as transportation and living quarters rather than simply food sources. They maintain the attachment across days, weeks, sometimes months. They don't damage the host. They provide minor benefits through incidental cleaning. The relationship becomes tolerated commensalism, one partner benefiting significantly, the other partner neither benefiting nor suffering, enough to make removal worthwhile. The goby fish and pistol shrimp create one of the ocean's most charming partnerships, cooperation between species, with vastly different capabilities, creating a household where each partner contributes specialized skills. The pistol shrimp, nearly blind, possesses remarkable digging ability. It excavates burrows in sandy substrate, using its claws to move sand grain by grain, creating tunnels and chambers extending deep below the surface. The work requires constant effort. Burrows collapse, sand fills spaces, maintenance never ends. But the shrimp persists, digging continuously, maintaining its home. The goby fish, with excellent vision but no digging ability, stands guard at the burrow entrance. It watches for predators, larger fish, octopuses, anything that might threaten the partnership. The shrimp keeps one antenna touching the goby's tail while working outside the burrow. If the goby spots danger, it flicks its tail. The antenna contact transmits the signal immediately. The shrimp retreats into the burrow within milliseconds, followed by the goby. They share the burrow. The shrimp digs, the goby watches, both gain protection. The shrimp couldn't safely forage outside without the goby's warning system. The goby couldn't maintain a burrow without the shrimp's digging. Together, they create a household neither could maintain alone. A partnership requiring communication and trust between species with completely different sensory capabilities. The relationship repeats across sandy areas throughout tropical and subtropical oceans. Multiple species of gobies partner with multiple species of pistol shrimp, each combination following the same basic pattern. Shrimp digs, goby watches, both benefit. The partnerships form quickly when both species are present, suggesting innate recognition of beneficial arrangements, instinctive cooperation programmed genetically, but expressed flexibly in response to local conditions. Coral polyps and zooxanthellae, algae-form partnerships so ancient and integrated that neither partner survives long alone in most cases. The relationship extends back millions of years, becoming so fundamental to both species that calling them partners understates the integration. They function as a single organism, though technically remaining separate species. The coral polyp, a tiny animal related to jellyfish and anemones, typically just a few millimeters across, secretes calcium carbonate, building the hard skeleton that forms reef structure. The polyp sits in a cup of its own creation, tentacles extended to catch zooplankton from passing water. But catching zooplankton provides insufficient energy for the polyp's needs, insufficient resources to build the massive reef structures that coral colonies create. The zooxanthellae algae live within the polyps, tissues, specifically within the cells, lining the polyp's gastrodermis, the inner tissue layer. These single-celled algae photosynthesize, using sunlight to convert carbon dioxide and water into sugars and oxygen. The coral polyp provides the algae with protected space, with nutrients from its waste products, nitrogen compounds, phosphorus, and with carbon dioxide from its respiration. The algae provide the polyp with sugars and oxygen. Up to 90% of the coral's energy comes from its algae partners. This arrangement allows corals to thrive in nutrient-poor tropical waters, where plankton concentrations remain low. The zooxanthellae essentially farm light, converting solar energy into chemical energy that powers the polyp's growth, reproduction, and reef construction. This partnership explains corals' dependence on shallow, sunlit water. Beyond roughly 60 meters depth, insufficient light reaches for photosynthesis. Without adequate light, zooxanthellae can't produce enough sugars. Without sugars from zooxanthellae, coral polyps can't build reefs. Reef-building corals must live where light penetrates, shallow water, clear water, water free of sediment that might block sunlight. The partnership also explains coral bleaching. When water temperatures exceed tolerance ranges for extended periods, typically just 2 to 3 degrees Celsius above normal summer maximums sustained for weeks, corals expel their zooxanthellae. The mechanism remains debated, but the result is clear. The coral turns white, the color of its calcium carbonate skeleton showing through now transparent tissue. Without zooxanthellae, the coral starves. It can survive for weeks on zooplankton alone, but this provides insufficient energy for growth or reproduction. If temperatures drop and zooxanthellae recolonize within a few weeks, the coral recovers. If bleaching extends for months, the coral dies, its skeleton becoming substrate for algae and other organisms. The reef structure persisting, but the living coral disappearing. Extended bleaching leads to reef collapse. Dead coral provides no shelter for juvenile fish. It produces no sound to attract larvae. The complex three-dimensional structure gradually erodes, waves and boring organisms, breaking down the calcium carbonate, reducing the reef to rubble. The entire ecosystem that depended on living coral, thousands of species of fish, invertebrates, algae, loses its foundation. The giant clam practices farming even more obviously than coral. These massive bivalves, growing over 4 feet long, weighing over 500 pounds, are the largest bivalves on Earth. They keep zooxanthellae in their mantle tissue, the fleshy, colorful tissue visible when the shell gapes open. The mantle displays extraordinary colors, blues, greens, purples, browns, created by different zooxanthellae strains and by light-scattering proteins in the clam's tissue. The clam positions itself with mantle exposed to sunlight. It essentially sunbathes, orienting to maximize light exposure for its algal farmers. The zooxanthellae photosynthesize, producing sugars that the clam absorbs and uses for energy. The clam filter feeds, as well, pumping water through its gills, straining out plankton and organic particles, but derives significant nutrition from its internal algae. This dual strategy allows giant clams to grow enormous. They settle as larvae barely visible to the naked eye. They grow slowly, perhaps 10 centimeters per year, but continuously across decades. A large giant clam might be 80 or 100 years old, having occupied the same spot on the reef for most of a century, filtering 50 liters of water per day while its zooxanthellae photosynthesize, creating a self-sufficient system requiring only sunlight, water flow, and patience. These partnerships, clownfish and anemone, cleaner and client, remora and shark, goby and shrimp, coral and zooxanthellae, clam and algae, demonstrate that cooperation creates opportunities impossible for individuals alone. The clownfish gains protection no solitary fish could achieve. The cleaner rasa builds a career on service no predator could maintain. The coral constructs reefs no single polyp could create. The giant clam grows to sizes no filter feeder could reach without photosynthetic supplements. In terrestrial environments, partnerships exist: pollinators and flowers, bacteria and ruminants, fungi and plant roots. But ocean symbioses often appear more visible, more dramatic, more fundamental to survival. Perhaps because the ocean's stability allows relationships to evolve across longer timescales. Perhaps because three-dimensional space and buoyancy create opportunities for partnerships that wouldn't work on land. Perhaps because we notice ocean partnerships more readily, their strangeness highlighting what terrestrial familiarity obscures. Regardless of explanation, the prevalence of ocean partnerships reveals something important: that cooperation works. That relationships built on mutual benefit, on specialized skills shared between partners, on trust maintained across repeated interactions. These relationships create stability, create productivity, create systems more resilient than individuals alone. Watch a clownfish family living in their anemone, 3 generations occupying the same tentacles, the oldest fish defending, while younger fish learn the partnership's subtleties. Watch cleaner wrasse servicing clients throughout the day, maintaining reputations through consistent quality, building careers on trustworthiness. Watch coral polyps spreading across reef substrate, each polyp connected to neighbors, sharing resources through colonial networks, building structures that persist for centuries. These partnerships teach patience, relationships develop slowly, trust accumulates gradually, benefits accrue over time rather than immediately. They teach specialization, each partner contributing what it does best, rather than attempting everything alone. They teach interdependence, recognizing that needing others isn't weakness but strategy. That cooperation often surpasses competition. That partnerships properly maintained outlast individuals, and in their stillness, the anemone rooted in place. The cleaner maintaining its station, the coral growing millimeter by millimeter. The clam filtering in one location for decades. These partnerships demonstrate that profound cooperation doesn't require constant activity. The most successful relationships often involve patient presence, reliable availability, trust, maintained through simple consistency rather than dramatic gesture. The ocean's partnerships will continue. The clownfish will remain in their anemones, generation after generation, occupying the same tentacles, maintaining relationships that benefit both partners across lifetimes. The cleaner rasa will continue servicing clients, building reputations through quality, demonstrating that even fish can practice hospitality. The coral will continue growing, polyp by polyp, creating reefs that support thousands of species. Structures built on partnerships between animals and algae. Cooperation so fundamental it becomes invisible until bleaching reveals its fragility. And we, observing these partnerships, receive yet another lesson from the ocean, that cooperation creates possibilities impossible alone, that partnerships properly maintained generate stability across time, that stillness and cooperation aren't opposites, but natural allies, both requiring patience, both benefiting from consistency, both creating systems that, once established, persist with minimal effort, sustained by mutual benefit rather than constant management. The ocean contains approximately 321 million cubic miles of water. 321 million cubic miles, enough to cover the entire Earth's surface to a depth of about 2.5 miles if spread evenly. Enough that if you could somehow remove all water from the ocean and distribute it uniformly across land and sea, standing anywhere on Earth's surface, you would find yourself under more than 2 miles of water, looking upward through darkness toward a surface you could never reach. 71% of Earth's surface hides beneath ocean waves. Nearly 3/4 of our planet consists of salt water, moving, breathing, teeming with life. We call our planet Earth, but perhaps we should call it ocean. The name would better represent the reality of our world's surface composition. This vast realm operates on principles fundamentally different from terrestrial existence. Gravity matters less. Buoyancy supports weight that would crush on land. Temperature changes slowly. Water's high specific heat capacity means the ocean absorbs and releases thermal energy gradually, creating stability that terrestrial environments rarely achieve. Sound travels farther. Acoustic connections span distances that would take months to swim. Movement requires less energy. Streamlined bodies gliding through dense medium encounter resistance, yes. But buoyancy eliminates the constant fight against gravity that dominates terrestrial locomotion. These physical differences created evolutionary pressures that favored efficiency over urgency, patience over panic, stillness over constant motion. In an environment where fighting gravity is unnecessary, where food often concentrates in predictable locations, where temperature remains stable across seasons, where predation occurs but doesn't dominate every moment, in such an environment, the optimal strategy isn't constant vigilance and frantic activity. The optimal strategy becomes patient efficiency, energy conservation, sustainable patterns of activity and rest maintained across long lifetimes. Life in the ocean spans nearly 4 billion years. 4 billion years, beginning with simple cells in ancient seas, evolving through countless forms, surviving mass extinctions that reshaped terrestrial life, persisting through ice ages and volcanic epochs and asteroid impacts. The ocean continued through all of it. Currents kept circulating. Water cycled between liquid and vapor. Marine life adapted and survived. This deep-time perspective reveals the ocean as Earth's most stable environment. Yes, conditions change. Ice ages affect ocean temperatures. Sea levels rise and fall. Currents shift patterns over millennia. But compared to terrestrial environments where seasons swing between extremes, where annual temperature ranges can span 60 or 80 degrees Celsius, where droughts and floods create unpredictable resource availability, compared to that variability, the ocean remains remarkably constant. Change happens gradually enough for adaptation to keep pace, creating creatures whose lifestyles reflect this fundamental stability. The Greenland shark living 400 years, the giant clam filtering water for a century, coral colonies growing for 500 years. These extreme lifespans become possible in environments where conditions remain reliably constant. Evolution can favor slow growth, late reproduction, extended lifespans, because environmental stability makes long-term strategies viable. The investment in a long life pays off when the environment doesn't shift dramatically enough to render that long life obsolete. Compare this to terrestrial life, where seasonal extremes, temperature swings, and resource variability favor shorter, faster-lived creatures. A rabbit lives 8 years, reproduces rapidly, exploits seasonal resources during brief periods of abundance. A mouse lives 2 years, produces multiple litters annually, survives through rapid reproduction rather than long life. Terrestrial environments often reward speed, grow fast, reproduce young, die before the next drought or winter or predation event. The ocean rewards patience, slow growth that conserves energy, late reproduction that waits for optimal size, long life that accumulates experience. The same strategies that would doom terrestrial creatures thrive in the ocean's stability. Now consider why ocean creatures calm humans, why watching fish lowers heart rates, why aquarium viewing reduces blood pressure, why ocean sounds help people fall asleep. The explanations reach into our evolutionary history. Human ancestors spent millions of years near coastlines. Evidence suggests early hominids gathered shellfish from tidal pools, fished in shallow waters, drank from rivers. Our brains evolved in environments where water meant resources and safety. Inland meant water scarcity, unpredictable food, potential danger. Coast meant reliable shellfish harvest, fish populations, fresh water from river mouths. Our neurology developed to associate water with positive outcomes. Food, safety, resources. Modern neuroimaging confirms this deep association. When people view aquariums or ocean scenes, brain scans show activation of the parasympathetic nervous system, the rest and digest system that promotes calm. Simultaneously, activity decreases in the sympathetic nervous system that drives fight-or-flight responses. These changes occur automatically, unconsciously. Heart rates slow measurably within minutes of viewing fish. Breathing deepens and becomes more regular. Cortisol levels drop over 30 to 60 minutes of aquarium viewing. These aren't learned responses. They're biological reactions, suggesting evolutionary connections between humans and water. Our bodies recognize water as good, safe, calming, not because we consciously believe this, but because millions of years of evolutionary history programmed these responses into our nervous systems. The specific blue wavelengths prevalent in ocean water affect human psychology through additional mechanisms. Blue light stimulates specialized ganglion cells in the retina, cells that don't contribute directly to vision, but instead feed information to brain regions regulating circadian rhythms and mood. These ganglion cells respond most strongly to blue wavelengths around 480 nanometers, exactly the wavelengths that dominate in clear ocean. Water. Studies measuring heart rate variability, a marker of nervous system. Balance indicating how well the body handles. Stress show that viewing blue colors produces more calming effects than viewing other hues. Red increases arousal. Yellow increases alertness. Green provides mild relaxation. Blue produces the strongest calming response, reducing heart rate variability toward patterns associated with relaxation and recovery. The ocean's dominant blue spectrum literally triggers neurological responses that promote relaxation. Even photographs of ocean scenes, even artificially created blue environments, produce measurable stress reduction. The wavelengths themselves communicate calm to our nervous systems, bypassing conscious interpretation, affecting us at levels we can't voluntarily control. Ocean sounds contribute additional calming effects through acoustic properties that match optimal human relaxation patterns. Wave sounds contain white noise characteristics, broad frequency spectrums without clear patterns that mask disturbing sounds while creating ambient soundscapes. The constant presence of sound prevents jarring silence, while the lack of clear patterns prevents our brains from trying to extract meaning or identify threats. The rhythm of waves hitting shores follows predictable patterns, typically 8 to 12 waves per minute, depending on wave period and beach characteristics. 8 to 12 cycles per minute coincides with optimal breathing rates for relaxation and meditation. Slow, deep breathing, the kind that activates parasympathetic responses, typically occurs at 6 to 10 breaths per minute. The ocean's wave rhythm naturally entrains breathing toward these calming patterns. Studies measuring brain activity during sleep show that ocean sounds increase slow wave sleep, the deepest sleep stage crucial for physical restoration and memory consolidation. People sleeping with ocean sound recordings spend more time in deep sleep, less time in light sleep, and report feeling more refreshed upon waking. The sounds don't put people to sleep faster necessarily, But they improve sleep quality once sleep begins. Whale songs contain infrasound, frequencies below 20 Hz, below human conscious hearing threshold. We can't hear these sounds in any traditional sense, yet they affect human physiology. Research suggests infrasound stimulates the vagus nerve, the major nerve connecting brain to heart, lungs, and digestive organs. Vagus nerve stimulation promotes parasympathetic activation, reducing heart rate, deepening breathing, enhancing digestion. People exposed to whale song recordings report feelings of awe and tranquility, even when they can't consciously hear the lowest frequencies. The mechanisms remain under investigation, but evidence suggests ocean creature vocalizations affect human listeners through multiple channels. Conscious audible frequencies that we hear and interpret. Subconscious infrasound that affects physiology without conscious awareness. And rhythmic patterns that entrain neural activity toward relaxation. The movement patterns of ocean creatures provide another calming element through visual mechanisms. The jellyfish pulsing at 60 beats per minute creates a rhythm close to resting human heart rate. The manta ray's slow wing flaps, perhaps 20 to 30 flaps per minute, create hypnotic rhythms that human visual systems track effortlessly. The whale's gentle tail strokes, 4 to 6 strokes per minute during casual swimming, create extremely slow rhythms that induce calm through their measured pace. These movements activate mirror neurons in human brains. Mirror neurons fire when we observe actions, creating neural echoes of the observed movement. Watching jellyfish pulse creates subtle neural rhythms, matching their movement frequency, essentially entraining brain activity to match the jellyfish's pace. Watching slow, rhythmic movements produces neural synchronization at those slow, rhythmic frequencies, brain waves literally synchronizing with the observed rhythm. This neurological synchronization produces measurable relaxation responses. Brain activity shifts toward patterns associated with meditation and deep relaxation. Muscle tension decreases. Cortisol levels drop. The relaxation occurs through observation alone, through visual input that drives neural synchronization that produces physiological changes throughout the body. The therapeutic applications of these findings continue expanding. Aquariums develop exhibits specifically designed for stress reduction, using species selection, prioritizing slow-moving fish. Jellyfish rays, lighting designed to maximize blue wavelengths, and layout informed by neuroscience research about optimal viewing angles and distances. Hospital waiting rooms install aquariums based on studies showing reduced patient anxiety and lower blood pressure in patients who spend time viewing fish before procedures. Dental offices place aquariums in treatment rooms, finding that patients viewing fish during procedures report less pain and require less anesthesia. Virtual reality therapy programs use ocean environments for treating anxiety disorders, PTSD, and specific phobias. Controlled studies show measurable improvement compared to control conditions. Patients using ocean-based VR therapy show greater symptom reduction than patients receiving standard talk therapy alone. The combination of visual input, sound design, and sometimes even simulated water movement creates immersive experiences that trigger the same neurological responses as viewing real oceans. Conservation efforts increasingly recognize the value of protecting ocean tranquility, not just for marine life, but for human well-being. Marine protected areas restrict boat traffic, reducing noise pollution that disrupts whale communication and navigation. Ships produce low-frequency sounds that travel long distances underwater, masking whale songs, interfering with echolocation, potentially causing chronic stress in animals that depend on acoustic communication. Quiet zones around critical habitats allow creatures like the North Atlantic right whale down to approximately 360 individuals, among the most endangered large whales, to rest, communicate, and raise young without constant acoustic interference. Speed restrictions in known right whale areas reduce ship strike mortality. These protections recognize that ocean peace benefits entire ecosystems, including humans who depend on healthy oceans for fisheries, climate regulation, and psychological well-being. The ocean's future faces unprecedented challenges. Warming temperatures shift species distributions, alter migration patterns, increase coral bleaching frequency. Ocean acidification, caused by oceans absorbing carbon dioxide from the atmosphere, reduces the ability of calcifying organisms to build shells and skeletons, threatening mollusks, corals, and the organisms that depend on them. Plastic pollution accumulates in ocean gyres, breaking down into microplastics that enter food chains at every level. Overfishing depletes populations of large predators, creating cascading effects throughout marine ecosystems. Yet the same stability that created tranquil ocean life also provides resilience. Coral reefs devastated by bleaching can recover if conditions improve and enough time passes. When water temperatures return to normal ranges, zooxanthellae recolonize. Coral polyps resume growing. Reef structure regenerates. The recovery takes years, sometimes decades, but it occurs if the fundamental conditions for survival return before coral colonies die completely. Fish populations rebound when protected from overfishing. Marine protected areas that prohibit fishing show rapid population increases. Fish biomass often doubling within 5 to 10 years of protection. Predator populations recover more slowly, but eventually return to sustainable levels. The ocean's productivity, when given respite from harvest pressure, demonstrates remarkable capacity for regeneration. Whales return to feeding grounds after decades of absence when conservation efforts reduce hunting pressure. Humpback whale populations in many regions have recovered substantially since commercial whaling ended, growing from thousands to tens of thousands. Their songs fill waters they hadn't inhabited in generations. Their presence affects entire ecosystems. Whale feces fertilizes surface waters, supporting plankton blooms, feeding fish, supporting seabirds, connecting deep ocean nutrients to surface productivity. The ocean's vast scale and ancient persistence suggest that protection efforts, even if imperfect, can preserve essential functions if implemented before critical thresholds are crossed. The ocean has survived worse than human impact. Asteroid impacts, massive volcanic eruptions, ice ages that froze surface waters hundreds of meters thick. Life persisted through all of it, adapting, evolving, surviving. The ocean's resilience isn't infinite, but it's substantial. Built through 4 billion years of facing and overcoming challenges, the lessons ocean creatures teach extend beyond their direct calming effects on human observers. They demonstrate that efficiency often surpasses speed. The blue whale, traveling 5 miles per hour, outlives and outsurvives faster creatures because sustainable pace matters more than maximum velocity. They demonstrate that patience can be a strategy rather than weakness. The Greenland shark, living 400 years, proves that extreme patience, far from being passive, represents sophisticated adaptation to environmental conditions. They demonstrate that communities built on cooperation survive longer than those built on competition. Coral reefs, built through partnerships between polyps and algae, between cleaner fish and clients, between countless species finding niches within the complex structure, persist for centuries, supporting thousands of species, creating productivity in nutrient-poor waters through cooperation rather than competition. The reef survives not because any individual species dominates, but because the system as a whole maintains balance through countless partnerships. The whale shark filtering plankton, the garden eel swaying in its burrow, the sea turtle returning to its birth beach after decades. Each represents a life strategy refined across millions of years, proven effective through eons of testing against the ultimate measure, survival. These strategies aren't inferior to terrestrial strategies, or less evolved, or less successful. They're simply different, adapted to different conditions, optimized for different environments. We return now to where we began, standing at the ocean's edge, gazing across blue vastness. But now we understand what those waters contain. Not just water and salt, but 4 billion years of evolutionary wisdom. Not just creatures, but teachers demonstrating how to exist in balance with fundamental forces. Not just an environment, but a mirror reflecting what we've lost and what we might reclaim. We've lost the knowledge that rest isn't weakness. Modern human culture often treats rest as laziness, as wasted time, as something to minimize in favor of constant productivity. But the ocean teaches otherwise. The sperm whale, sleeping vertically, completely unconscious, demonstrates that profound rest isn't optional. It's essential. The manatee resting 20 hours daily shows that most of life can be rest. Activity concentrated into brief periods of feeding. The remainder dedicated to restoration. We've lost the understanding that patience isn't passive. We see patience as simply waiting, as accepting whatever happens, as lacking agency. But the ocean teaches otherwise. The sea star pulling at a clamshell for hours demonstrates active patience, sustained effort at sustainable intensity, persistence that outlasts resistance. The Greenland shark, living 400 years, shows that patience operates at scales we barely comprehend, that life strategies can span centuries, that our human sense of urgency reflects our short lifespans rather than any objective truth about how life must be lived. We've lost the recognition that tranquility isn't the absence of life, but its most refined expression. We associate calm with stillness approaching death, with reduction of activity toward nothing. But the ocean teaches otherwise. The blue whale's heart, beating twice per minute during dives, represents not near death, but optimization. The whale remains fully alive, fully aware, simply operating at maximum efficiency. The Nautilus, maintaining neutral buoyancy through precise chamber adjustments, demonstrates that tranquility requires sophisticated control, constant tiny adjustments that maintain calm through active management rather than passive acceptance. The ocean continues its eternal rhythms, whether we witness them or not. Jellyfish pulse through the same waters they've inhabited for 500 million years. Their simple bodies proving that complexity isn't required for persistence. Whales sing songs across ocean basins, compositions evolving slowly, connecting individuals across distances that dwarf any terrestrial migration. Corals grow millimeter by millimeter, building structures that persist for centuries, creating cities of shelter where thousands of species find homes. The humpback makes its 5,000-mile migration, mother and calf swimming slowly southward, arriving when they arrive. The journey itself being the life. The hagfish scavenges on the seafloor, unchanged for 300 million years, demonstrating that perfection reached long ago requires no improvement. The manta ray visits its cleaning station, receiving service from fish small enough to swallow, trusting in partnerships refined across millennia. All of this happens whether we witness it or not, whether we understand it or not, whether we protect it or not. But in choosing to witness, we grant ourselves access to something rare in modern existence. In choosing to understand, we connect to rhythms older than our species, deeper than our concerns, more patient than our lives. In choosing to protect, we acknowledge that these rhythms matter, that this wisdom deserves preservation, that the ocean's lessons remain relevant to creatures, ourselves, who evolved on land but carry the ocean within us still. We discover that the ocean's peace isn't something we observe from outside, something separate from our lives, something available only to those who can visit coasts or afford aquarium tickets. The ocean's peace exists within us already, written into our neurology through millions of years of evolutionary history, accessible whenever we remember to slow down, to breathe deeply, to surrender to rhythms larger than our immediate concerns. When we watch jellyfish pulsing, our hearts slow to match their rhythm. When we hear whale songs, our nervous systems respond to frequencies we can't consciously hear. When we view ocean blue, our brains shift toward patterns associated with calm. These responses occur automatically because they're built into our biology, inherited from ancestors who understood what we've forgotten, that water means safety, that blue means calm, that rhythms matching natural patterns restore what urgency depletes. The ocean offers us a portal. Not a physical portal requiring travel, though visiting the ocean certainly helps, but a conceptual portal, available through memory, through imagination, through the simple act of remembering what the ocean teaches. When stress overwhelms, when urgency demands attention we don't have, when the relentless pace of modern life becomes unbearable, in those moments, we can remember the blue whale's heart beating twice per minute. We can remember the Greenland shark moving at less than 1 mile per hour. We can remember that somewhere, right now, a sea turtle swims steadily homeward, breathing once every 5 hours, traveling 3,000 miles without hurry. These memories, even second-hand, even learned rather than experienced, trigger the same neurological responses as direct observation. Our brains don't fully distinguish between remembered ocean and observed ocean. Both activate parasympathetic responses. Both shift brain activity toward relaxation. Both remind us that urgency isn't the only option, that speed isn't the only strategy, that the qualities we most need, patience, efficiency, tranquility, exist not as abstract ideals, but as living realities practiced by creatures who have perfected these arts across millions of years. The ocean will continue teaching whether we learn or not. The lessons remain available, broadcast constantly through the lives of creatures who embody them. The blue whale will continue its slow cruising, demonstrating that the largest animal ever to exist thrives on minimal cardiac activity. The octopus will continue changing colors while sleeping, possibly dreaming, its brief, intelligent life burning brightly before extinguishing, showing that even intelligence must sometimes surrender to natural cycles. The manatee will continue grazing peacefully on seagrass, unbothered and unhurried, proving that long lives of gentle existence remain viable strategies despite, or perhaps because of, their complete lack of urgency. The coral will continue growing, polyp by polyp, building reefs that support thousands of species, creating structures through partnerships so integrated that individual boundaries become meaningless, and we, if we're wise, will continue learning. We'll visit aquariums not just for entertainment, but for restoration, recognizing that viewing fish provides measurable health benefits, that the time spent watching jellyfish pulse constitutes genuine self-care. We'll protect marine environments not just for the creatures living there, but for ourselves, acknowledging that ocean health affects human health. That quiet zones benefiting whales also benefit humans seeking peace. We'll remember, in moments when urgency threatens to overwhelm, that there exist other ways to move through the world, that vast distances become manageable when divided into patient increments, that success often comes through waiting rather than chasing, that the qualities we most desperately need, calm, patience, efficiency, balance, aren't mysterious secrets requiring years of practice to access. They're our birthright, inherited from ancestors who understood what the ocean teaches, available whenever we remember to breathe deeply, to slow down, to surrender to rhythms that have sustained life for 4 billion years. The ocean covers 71% of Earth's surface, 321 million cubic miles of water, containing more life than all terrestrial environments combined, operating on principles refined across billions of years. This isn't decoration on our planet. This is our planet's dominant feature, the environment that created life, the realm that still demonstrates how existence can be practiced when efficiency matters more than speed, when patience proves more viable than urgency, when tranquility represents not the absence of life, but its most refined expression. Standing at the ocean's edge, we face a choice. We can see water, interesting, beautiful, but separate from our lives, relevant only to creatures adapted for aquatic existence. Or we can see teachers, billions of them, each demonstrating some aspect of wisdom we desperately need, each practicing arts we've forgotten, each offering lessons available to those willing to watch, to listen, to learn, the jellyfish pulsing, the whale sleeping vertically, the sea turtle navigating across oceans, the shark waiting for sleeping seals, the eel swaying in its burrow, the clownfish safe among anemone tentacles, the cleaner fish building reputations, the coral growing imperceptibly, the clam filtering patiently, each creature a teacher, each life a lesson, each example proof that tranquility isn't weakness, patience isn't passivity, stillness isn't the absence of life, but can be its most sophisticated expression. We carry the ocean within us, salt in our blood, water in our cells, evolutionary history connecting us to ancestors who emerged from seas 400 million years ago. We carry the ocean's wisdom within us too, buried under layers of cultural learning that told us speed matters most, urgency defines success, constant activity prevents falling behind. But the buried wisdom remains accessible, waiting for us to remember, to recognize, to reclaim what we never truly lost. The ocean teaches that rest is strength, that patience is power, that efficiency surpasses speed, that balance persists longer than extremes, that cooperation creates possibilities impossible alone, that stillness in motion, the art that ocean creatures have perfected, represents not contradiction, but integration, not impossible paradox, but achievable reality. These lessons, practiced by billions of creatures across 4 billion years, tested against the ultimate measure of survival and proven effective across timescales that dwarf human civilization, these lessons remain available. The teachers remain willing. The ocean continues broadcasting its wisdom, inviting us to witness, to understand, to carry these truths into our own lives, and in that carrying, in that integration of ocean wisdom into human experience, we discover something remarkable. We discover that the peace we seek doesn't require perfection. It doesn't require living like whales, or swimming like fish, or abandoning everything that makes us human. It requires only remembering what the ocean teaches, that beneath the surface urgency, beneath the cultural demands for constant productivity, beneath the anxiety that modern life generates, beneath all that lies something older, deeper, more fundamental. There lies the knowledge that we are, like ocean creatures, products of evolution that favored efficiency, that rewarded patience, that built survival strategies around balance rather than extremes. There lies the recognition that our most peaceful moments come when we surrender to rhythms larger than ourselves, breathing that slows toward ocean wave frequencies, movement that becomes deliberate rather than rushed, existence that prioritizes being overdoing. There lies the understanding that tranquility isn't something we achieve through effort, but something we allow through surrender, surrendering urgency, surrendering the belief that speed equals success, surrendering to the simple truth that the ocean has known for 4 billion years, that in stillness there is motion, in patience there is power, in rest there is restoration, and in learning from creatures who have perfected these arts, there is hope for creatures, ourselves, who desperately need to remember what we've forgotten. The ocean continues its eternal rhythms. The lessons remain available. The teachers persist in their patient demonstrations. And we, standing at the water's edge, or lying in beds far from any coast, can close our eyes and remember the blue whale's heart beating twice per minute, the jellyfish pulsing 60 times per minute, the sea star pulling at shells for hours, the Greenland shark living 400 years, the ocean itself, ancient, patient, persistent, peaceful, offering us, generously and continuously, the wisdom we need to find our way back to stillness, back to balance, back to the art that ocean creatures have perfected and graciously, endlessly offer to teach.